Hello and welcome to Space Historians. I'm so glad you found your way here tonight, ready to let the day's noise fade into something quieter, something larger. Tonight, we're embarking on a journey that begins with a simple question, but one that opens into vastness. How long would it take to cross our galaxy? It sounds straightforward, doesn't it? The kind of question you might ask while lying on your back, gazing at the Milky Way stretched across a dark sky. But the answer, when you start to unpack it, reveals distances and timescales that challenge everything we think we understand about travel, about time, about what's possible. Before we drift outward together, I'd love to know, where in the world are you right now? Can you see stars from where you are? Or is it daylight streaming through your window? Are you tucked beneath blankets or sitting quietly in a chair? Wherever you find yourself, you and I are sharing this moment, connected across distance by curiosity and starlight. If you enjoy these slow journeys through cosmic questions, a gentle like or a quiet subscription helps keep this small corner of wonder alive. For those who've already joined this constellation of listeners, thank you. You're part of this voyage. Tonight's question isn't about equations or spacecraft specifications, though we'll touch on those. It's about scale. It's about confronting the reality that our home, the Milky Way, is so vast that even light itself, racing at the universe's speed limit, needs 100,000 years to travel from one edge to the other. 100,000 years. Think about that for a moment. All of recorded human history, every civilization that has risen and fallen, every language spoken, every monument built, all of it fits into just a fraction of that time. And that's at the speed of light, faster than anything with mass can ever travel. So, as your breathing slows, as your thoughts begin to drift, imagine yourself stepping back from Earth. Not quickly, not with urgency, but gently. Watch our blue planet shrink to a pale dot. Watch the sun become just another star among billions. And ahead of you stretches the Milky Way, a spiral of light and darkness, 100,000 light years from edge to edge. Tonight, we're going to measure that distance in every way we can imagine. We'll ride alongside photons of light. We'll calculate the journey times for spacecraft. We'll dream of generation ships and ponder the strange gift of time dilation. And we'll confront the humbling truth that some distances are so vast they reshape what the word journey even means. If you tap that notification bell, you'll know when the next exploration begins. But for now, there's nothing you need to do except listen, breathe, and let yourself wonder. The galaxy is waiting, not to be crossed perhaps, but to be understood. And understanding, as we'll see, is its own kind of crossing. Welcome to the edge of forever, somewhere on the far side of the Milky Way. At this very moment, a photon of light is beginning a journey. It leaves the surface of a star, one among billions, and strikes out into the darkness. It moves at 300,000 kilometers per second, the fastest speed the universe allows. Nothing can overtake it, nothing can match its pace. And yet, even at this ultimate velocity, that photon will not reach our side of the galaxy for 100,000 years. 100,000 years. Let that settle for a moment. If that photon had begun its journey when the first humans were painting on cave walls, when our ancestors were just learning to control fire and shape stone tools, it would still be travelling today. It would be only part way through its crossing, with tens of thousands of years still ahead. This is the hook, the impossible truth that draws us into tonight's question. The Milky Way, our home galaxy, is so vast that even light, the ultimate traveller, the fastest thing in existence, needs longer than all of human civilization to make the crossing. When we ask how long it would take to cross the galaxy, we're not asking an idle question. We're confronting scale itself. We're measuring ourselves against distances that dwarf everything we know. Consider what 100,000 years means in human terms. Go back 100,000 years and you find Homo sapiens in Africa, not yet spread across the world. There were no cities, no agriculture, no written language, no nations. The species existed, but barely, clinging to survival in a world of predators and ice ages. Now imagine someone from that time, somehow preserved and brought forward to today. Everything would be unrecognizable. The continents themselves would look different. The climate would have shifted through ice ages and warm periods. Entire species would have come and gone, and humanity would have transformed beyond imagination. That span of time, longer than our entire history, is what light needs to cross the galaxy. Not us, not our spacecraft. Light itself, the fastest messenger in the cosmos. This truth was discovered gradually, pieced together over centuries of observation. Ancient humans saw the Milky Way as a river of light across the sky, a path for gods or souls. They had no idea they were looking at a structure from inside, seeing the edge on view of a disk containing billions of stars. It wasn't until the 20th century that astronomers measured the true scale. Using stars that pulse with predictable brightness, they calculated distances. Using careful observations of star motions, they mapped the structure. And slowly, the picture emerged. The Milky Way is a spiral galaxy, shaped like a disk with graceful arms curling outward from a bright central bulge. From edge to edge across that disk, the distance is roughly 100,000 light-years. Some measurements suggest 90,000, others stretch it to 120,000. The exact number varies with technique and definition, but the order of magnitude remains the same. 100,000 light-years. 100,000 times the distance light travels in a year, each year containing nearly 10 trillion kilometers. The numbers grow so large they lose meaning. Our minds aren't built to grasp such scales. We understand a kilometer. We can imagine 1,000 kilometers. We can barely conceive of 1,000,000. But 10 trillion? Multiplied by 100,000? The galaxy defies comprehension. And yet we live inside it. Every breath you take, every heartbeat, every thought occurs within the Milky Way. You are not separate from this vast structure. You're part of it, a participant in its slow rotation around the centre, a temporary arrangement of atoms that happens to be conscious within a system larger than imagination allows. The photon we imagined at the beginning of this chapter will continue its journey long after we're gone. It will pass through clouds of gas and dust. It will skim past stars, perhaps illuminating planets we'll never know exist. It will cross the arms of the spiral, moving through regions where stars are being born and dying. And if, somehow, it reaches our corner of the galaxy, if it happens to strike a telescope or an eye, it will have completed an odyssey spanning timescales we can barely measure. The star it left behind will have aged. The galaxy itself will have rotated slightly, and the beings who receive that light, if any remain, will be looking at an image from the deep past. This is what crossing the galaxy means at the most fundamental level. Not a trip you complete, not a destination you reach, but a span of time so vast it contains civilizations, species, and epochs. When we talk about crossing the galaxy, we're really asking, what does it mean to move through a structure measured in eons? What does travel look like when even light, tireless and swift, needs longer than recorded history to complete the journey? The galaxy is not a place you visit. It's a context you exist within. The question of how long it takes to cross is less about finding an answer and more about understanding scale, about recognizing that our intuitions about distance and time break down at cosmic scales. Tonight, we're going to explore that breakdown. We'll measure the crossing in every way we can imagine. We'll start with light, the benchmark. We'll move to spacecraft, the machines we've actually built. We'll dream of faster ships, generation vessels, and exotic physics that might, just might, offer shortcuts. But we'll begin here with the simple, impossible truth. A photon leaves one edge of the galaxy. 100,000 years later, if nothing stops it, it might reach the other side. That journey, impossible for us but routine for light, sets the stage for everything that follows. Because if the fastest possible traveller needs that long, then anything slower needs longer. And we, bound by mass and engineering and the limits of human lifespans, are much, much slower. The galaxy stretches before us, 100,000 light-years wide, a spiral of stars and darkness, too vast to cross in any human time frame, but not too vast to wonder about. That wonder, that curiosity about the impossible, is what brings us together tonight. And as we drift deeper into the question, as we measure and calculate and dream, we'll find that even asking how long becomes a meditation on our place in the universe. The photon continues its journey. 100,000 years from now, it will still be travelling. And we, here in this moment, can only imagine what that journey looks like, stretched across timescales that dwarf our existence but define our home. The galaxy is patient. It has been here for billions of years, will remain for billions more. Our questions about crossing it are brief sparks of curiosity in a cosmos that measures time differently than we do. But those sparks matter. They illuminate not just the distance, but our desire to understand it, to place ourselves within it, to ask what's possible even when the answer is nearly nothing. And that desire, that reaching toward the impossible, is what makes us human. It's what makes us look up at the Milky Way band stretched across a dark sky and ask not just, what is that? But how long would it take to cross it? The answer will unfold across this night, across these chapters, measured in light years and centuries, in physics and dreams, in the slow recognition that some distances are meant not to be travelled, but to be comprehended, appreciated, and held gently in the mind as reminders of how vast our home truly is. To understand how long it would take to cross the galaxy, we first need to know where we're starting from, and that means understanding where we are. Earth doesn't sit at the centre of the Milky Way. We're not nestled in the bright, crowded core where stars pack together by the millions, nor are we drifting at the sparse, lonely edges where the spiral arms thin into darkness. We're somewhere in between, a comfortable middle ground, orbiting an ordinary yellow star in a modest arm of the spiral, and from this vantage point, inside the structure we're trying to measure, we face a challenge that astronomers have wrestled with for centuries. How do you map a forest when you're standing among the trees? Our sun lies approximately 27,000 light-years from the galactic centre. That distance alone is staggering. 27,000 times the span light covers in a year. If you could somehow travel at light speed toward the centre, you'd arrive 27,000 years from now, around the time humans on Earth were living in the Stone Age. But we're not just stationary at this distance. The Sun, carrying Earth and all the planets with it, orbits the centre of the galaxy. We move at roughly 230 kilometres every second, swept along in a great circuit that takes about 230 million years to complete. Think about that orbital period. The last time the Sun was in its current position in the galaxy, dinosaurs walked the Earth. The continents were arranged differently. The climate was warmer. Mammals were small, insignificant creatures scurrying beneath the feet of giants. One orbit of the galaxy, one cosmic year, is longer than the entire age of the dinosaurs. We live in what's called the Orion Arm, sometimes called the Orion Spur. It's not one of the major arms of the galaxy. Those belong to Perseus and Sagittarius, vast sweeping structures where star formation is active and vibrant. Our arm is smaller, a kind of bridge between the larger structures, but smaller is relative. The Orion Arm stretches thousands of light years. Within it are nebulae where stars are being born, clusters of young blue giants, and ancient red stars nearing the end of their lives. The arm contains everything we can see with the naked eye. Every constellation, every star you've ever named, exists within this local structure. From our position, the galaxy appears as a band of light across the sky. This is because we're looking at the disk edge on, seeing the concentration of stars, gas, and dust that defines the spiral. When you gaze at the Milky Way on a clear night, you're seeing the combined light of billions of stars too distant to resolve individually, all merged into a soft glow. The brightest part of that band points towards Sagittarius, toward the centre of the galaxy. There, 27,000 light-years away, lies the heart of our cosmic home. At its core sits Sagittarius A star, a supermassive black hole containing about 4 million times the mass of the Sun. We cannot see it directly. Dust clouds block our view in visible light, but radio telescopes and infrared instruments peer through the obscuring material, revealing the churning chaos of the center. Stars orbit the black hole at tremendous speeds, pulled by gravity into tight loops that take years or decades to complete. That central region is nothing like our neighborhood. Stars there are packed far more densely. Encounters between stellar systems are more common. Radiation levels are higher. If Earth somehow found itself near the core, the night sky would be ablaze with stars, thousands visible to the naked eye, so bright you could read by their light. But we're far from that intensity. Out here in the Orion Arm, the spacing between stars is comfortable. The nearest star system, Alpha Centauri, lies over 4 light-years away. That's a vast gulf, but it's typical for our region. We have room, space to exist without interference, without the gravitational chaos of the crowded center. This position has advantages. We're in what some astronomers call the galactic habitable zone, far enough from the core to avoid its dangers, but close enough that the disk contains heavy elements, the metals and complex atoms necessary for rocky planets and life as we know it. The outer edges of the galaxy, beyond the bright spiral arms, are quieter still. Stars there are older, redder, more spread out. The rate of star formation drops. The material for building new worlds grows scarce. We live in a sweet spot, a region where conditions allow for stability and complexity. Understanding our position helps frame the crossing. If we wanted to travel to the galactic center, we'd need 27,000 years at light speed. To reach the far side of the disk from here would take 73,000 years, still at that ultimate velocity. And to go all the way across, from one edge through the center to the opposite edge, we return to our benchmark, 100,000 years. But our position isn't just spatial, it's also temporal. We exist at a particular moment in the galaxy's history. The Milky Way is about 13 billion years old, formed not long after the Big Bang. It has cycled through generations of stars, each one enriching the interstellar medium with heavier elements. The Sun itself is a third-generation star, born from gas clouds that contain the remnants of earlier stars. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it was forged in stars that lived and died before our Sun ignited. We're not just inside the galaxy spatially, we're embedded in its history, products of its long evolution from a cloud of hydrogen and helium into a structured spiral filled with complex chemistry. From this setting, from our place in the Orion Arm, we look outward and try to comprehend the whole. We send telescopes into space to peer through dust. We launch probes that drift for decades, reporting back on the local environment. We build radio dishes to detect faint signals from the far reaches. And slowly, over centuries, the map has come together. We know the galaxy is a barred spiral, with a central bar of stars stretching across the core. We know the arms wind outward in, a pattern shaped by density waves, regions where stars and gas compress and then move onward. We know the disk is thin relative to its width, only about 1,000 light-years thick in the main star-forming regions, but 100,000 across. We know that surrounding the disk is a halo, a spherical cloud of old stars and dark matter extending far beyond the visible structure. And we know that the galaxy doesn't exist in isolation. It's part of a local group, bound by gravity to Andromeda and dozens of smaller galaxies. In a few billion years, Andromeda and the Milky Way will merge, creating a new, larger structure. Our position will shift, the setting will change, but for now, we're here. 27,000 light-years from the center, orbiting at 230 kilometers per second, part of a spiral arm that stretches across thousands of light-years, looking out at a structure we're embedded within, trying to measure its scale from inside. This is the setting for our journey, not a journey of motion, not yet, but a journey of understanding. Because before we can ask how long it takes to cross, we need to know what we're crossing and where we're starting from. The galaxy is vast, but it's also knowable. From our position, limited as it is, we've mapped the structure, measured the distances, traced the spiral. We've done this with light, with patience, with centuries of accumulated observation. And that setting, that local vantage point in the Orion arm of a barred spiral galaxy, is where the question begins. Not from some abstract outside view, but from here, from a small planet orbiting a medium star, looking up at the band of light that is our home and asking, how far does it stretch? How long would it take to cross? The answer starts with knowing where we stand. And we stand in the middle, comfortable and modest, surrounded by stars yet isolated from most of them by distances that light takes years to span. This is our place. This is the setting. And from here, we begin the calculation, the slow realization of scale that will unfold across the rest of this night. The Orion arm, our home, is itself a journey in progress. As the galaxy rotates, we sweep through different regions of space, encountering denser clouds of gas, passing near stellar nurseries, moving through quiet voids. Our setting is not fixed but flowing, a dynamic position in a structure that never stops moving. And perhaps that's fitting, because when we ask how long it takes to cross the galaxy, we're really asking about motion relative to motion, distance measured within a system that is itself in constant flux. We orbit the center. The center orbits within the broader structure of the local group, and the local group drifts through space at speeds we're only beginning to measure. Our setting is a snapshot, a moment in time, a single frame in a story billions of years long. But it's the only setting we have, the only vantage point from which to measure. And from this modest arm, this comfortable distance from the chaos of the core, we can still see the whole, can still map the spiral, can still ask how long it would take to traverse what we've measured. That ability to see the forest despite standing among the trees is perhaps our greatest achievement. And it starts here, in the setting, in the knowledge of where we are. For most of human history, the Milky Way was a mystery wrapped in myth. Ancient peoples saw the pale band of light stretching across the night sky and wove stories to explain it. The Greeks called it the Milk of Hera. The Chinese saw it as a silver river. Norse mythology described it as a path to Valhalla. Beautiful stories, all of them, but none came close to the truth. The truth was far stranger. That band of light wasn't milk or a river or a path. It was the combined glow of billions of stars, so distant and numerous that they merged into a soft haze. And we weren't looking at something separate from us. We were looking at our home from inside it, seeing the disk of the galaxy edge on. Understanding this took centuries, and measuring the true scale of that structure took even longer. The story of how we mapped the Milky Way is a story of incremental progress, brilliant insights, and the slow accumulation of evidence. It begins with Galileo Galilei in 1610. When he turned his primitive telescope toward the Milky Way, he made a discovery that would reshape astronomy. The hazy band resolved into countless individual stars. What appeared to the naked eye as a smooth glow was actually a vast multitude of distant suns. This was revolutionary. It suggested that the universe was far larger and more populated than anyone had imagined. But Galileo couldn't measure distances. He could only observe that the Milky Way was made of stars, not some celestial substance. The question of scale remained unanswered. In the 18th century, William Herschel, working with his sister Caroline, attempted the first systematic mapping. Herschel's method was simple. Count stars in different directions. He assumed that if you saw more stars in one direction, that region must be thicker, denser, or closer. Based on his counts, Herschel concluded that the Milky Way was a flattened disk with the sun near its centre. He was correct about the disk shape, but he was wrong about our position. The sun is not central. It's far out in one of the arms. Why was Herschel wrong? Because dust. Thick clouds of interstellar dust absorb and scatter light, making distant regions appear empty even when they're not. Herschel's counts were biased by what he could see, and he couldn't see through the obscuring material. Still, his work was a beginning. It established that the Milky Way had structure, that it was a bounded system rather than an infinite expanse. The next breakthrough came in the early 20th century, through the work of Henrietta Leavitt. She studied a type of variable star called Cepheids, which pulse in brightness with predictable periods. Leavitt discovered a relationship. The longer a Cepheid's period, the brighter its intrinsic luminosity. This was powerful. If you knew how bright a Cepheid should be and you measured how bright it appeared, you could calculate its distance. Cepheids became standard candles, cosmic lighthouses that allowed astronomers to measure distances across vast spans. Using Leavitt's discovery, Harlow Shapley mapped the distribution of globular clusters, dense spheres of ancient stars that orbit the Milky Way. He found that these clusters were concentrated in one direction, towards Sagittarius, and their distances, calculated using Cepheids, were enormous, tens of thousands of light-years. Shapley realized what this meant. The globular clusters weren't evenly distributed around Earth. They were evenly distributed around the galaxy's center. And that center was not where the Sun sat. It was 27,000 light-years away, in the direction of Sagittarius. This was a profound shift. Humanity had already been displaced from the center of the solar system by Copernicus. Now Shapley displaced us from the center of the galaxy. We weren't special. We were off to the side, in the suburbs of the Milky Way. Shapley's work also provided the first reliable estimate of the galaxy's size. He calculated that it was about 100,000 light-years across, a number that has been refined but not radically changed in the century since. But there was still more to learn. The structure of the galaxy, its spiral arms, its central bar, remained hidden. Optical telescopes couldn't see through the dust. For a fuller picture, astronomers needed to look in wavelengths that dust doesn't block. Radio astronomy provided that view. In the 1950s, astronomers mapped the distribution of neutral hydrogen gas, which emits radiation at a wavelength of 21 centimeters. This radiation passes through dust clouds, revealing structure that optical light cannot show. The radio maps revealed the spiral arms. The Milky Way wasn't just a disk. It was a barred spiral, with graceful arms winding outward from a central elongated structure. Our position in the Orion arm became clear, as did the layout of the larger Perseus and Sagittarius arms. Infrared observations added more detail. Infrared light, like radio waves, penetrates dust better than visible light. Infrared surveys showed the densely packed stars of the central bulge, the bar stretching across the core, and the warp in the disk where gravitational interactions with smaller galaxies have bent the structure. Each new wavelength revealed another layer. X-ray telescopes showed high-energy phenomena, the remnants of supernovae, the accretion disks around black holes. Gamma-ray observations highlighted the most violent processes, the explosions and collisions that shaped the galactic environment. But the most detailed map came from Gaia, launched by the European Space Agency in 2013. Gaia is a space telescope designed to measure the positions and motions of stars with extraordinary precision. It has tracked over 1 billion stars, creating a three-dimensional map of the Milky Way. Gaia's data show not just where stars are now, but where they're moving. By tracking their velocities, astronomers can trace their orbits backward and forward in time. They can see how the galaxy rotates, how the arms evolve, how streams of stars mark the remnants of smaller galaxies that merged with the Milky Way long ago. Gaia confirmed the size. The disk is roughly 100,000 light-years across. It refined our understanding of the Sun's position. 27,000 light-years from the center, moving at 230 kilometers per second, and it revealed fine structure, ripples and warps in the disk, that suggest the galaxy's history is more violent than we once thought. Mapping the Milky Way from inside it has been one of the great achievements of astronomy. We've done it without ever leaving our solar system, without ever gaining an outside view. We've done it with light, with patience, with clever techniques that turn faint signals into precise measurements. And through that mapping, we've come to understand the scale of our home. 100,000 light-years, billions of stars, a structure so vast that even travelling at light speed, the crossing takes longer than human civilization has existed. This discovery, this slow realization of scale, is what allows us to ask the question we're exploring tonight. Without the measurements, without the maps, the question would be meaningless. We'd have no idea what we were crossing or how far it stretched. But now we know. The Milky Way is immense. Its disk spans 100,000 light-years. Its halo extends even farther, and our position within it, modest as it is, has been precisely located. The discovery of the galaxy's scale was not a single moment. It was a process, stretching across centuries, involving hundreds of astronomers and countless observations. Each generation refined the measurements, added detail, corrected errors, and the process continues. New telescopes, new techniques, new missions will refine the map even further. We'll discover more about the dark matter halo that surrounds the visible structure. We'll trace the galaxy's history more precisely, understanding how it formed and evolved. We'll measure the distances to the farthest stars with greater accuracy. But the broad picture is clear, and that picture sets the stage for everything that follows. Because now that we know the galaxy's size, we can calculate how long it would take to cross it. We can compare different speeds, different technologies, different dreams. The discovery of the Milky Way's scale was the first step, and it revealed a truth that shapes all our subsequent calculations. The galaxy is vast beyond ordinary comprehension. Light itself, racing at the cosmic speed limit, needs 100,000 years to make the crossing. That discovery, that measurement, is where the question becomes real. Not abstract, not philosophical, but grounded in numbers. 100,000 light years, and from that number we can begin to calculate what the crossing would mean for travellers moving slower than light, much slower, at speeds bound by mass and energy and the limits of engineering. The map has been drawn. The distance is measured. And now, with those measurements in hand, we can ask, how long would it take, not just for light, but for us, with our machines, our limitations, our dreams of reaching across the vast spiral we call home? When Harlow Shapley first calculated the size of the Milky Way in the early 20th century, the reaction among astronomers was a mixture of excitement and disbelief. 100,000 light-years. The number was so large it seemed almost absurd. Before Shapley's work, estimates of the galaxy's size were far smaller. Many astronomers thought the Milky Way might be only a few thousand light-years across. Some believed the Sun was near the centre. The universe itself seemed compact, comprehensible. Shapley's calculations shattered that comfortable view. The galaxy was 10, 20, even 50 times larger than previous estimates, and the Sun wasn't central at all. It was off to one side, just another star in a sea of billions. The immediate response was wonder. How could something so vast exist? How could we, tiny and brief, be part of a structure measured in such immense distances? But wonder was quickly followed by a more practical realization. If the galaxy was that large, then the distances between stars were equally vast. And if distances were vast, then the dream of travelling between stars, already challenging, became almost impossibly difficult. Consider the human experience of distance. We evolved to understand spans we could walk. A kilometre is comprehensible. We can walk it in 10 or 15 minutes. 100 kilometres is a day's travel on foot. 1,000 kilometres might take a week. Even with modern technology, distances remain grounded in experience. A flight across an ocean takes hours. A trip to the moon takes days. A journey to Mars, with current spacecraft, takes months. But light years? 1 light year is nearly 10 trillion kilometres. It's a distance so large that no human experience prepares us for it. Even the nearest star, Alpha Centauri, lies over 4 light-years away. At the speed of our fastest probes, it would take tens of thousands of years to reach it. And the galaxy? 100,000 light-years across. Multiply that incomprehensible light-year distance by 100,000. The result is a number that exists only as abstraction, a figure on paper without any connection to lived experience. When Shapley announced his findings, some astronomers resisted. Not because his mathematics were wrong, but because the implications were so vast they felt uncomfortable. If the galaxy was that large, it meant humanity's cosmic significance was even smaller than Copernicus had shown. We weren't just displaced from the center of the solar system. We were displaced from the center of the galaxy. We were far out in the suburbs, in a minor arm, orbiting at a comfortable but unremarkable distance from the core. And if our position was unremarkable, what did that say about us? About our place in the universe? About the likelihood that we were alone? These were philosophical questions, but they arose directly from the scale. The sheer size of the Milky Way forced a confrontation with our own smallness, and for some, that was difficult to accept. But for others, the wonder deepened. Yes, the galaxy was vast. Yes, we were small, but we were also capable of measuring it. From our tiny vantage point, using nothing but light and clever mathematics, we had determined the size of our cosmic home. That ability, that capacity to reach beyond our immediate surroundings and comprehend the larger structure, was itself extraordinary. The galaxy might be immense, but we could know it. We could map it. We could understand our place within it. The first response to the discovery of scale was not despair, but awe. And with awe came questions. If the galaxy was this large, how many stars did it contain? How many planets? How many places where life might arise? Astronomers began to calculate. If the Milky Way was 100,000 light-years across, and stars were spaced a few light-years apart, then the galaxy must contain billions of stars. The exact number was uncertain, but the order of magnitude was clear. We live in a galaxy of billions, not thousands, not millions, billions, each one a sun, potentially with planets of its own. That realization transformed astronomy. The universe was not sparse, it was teeming, and if our galaxy alone contained billions of stars, and if there were billions of other galaxies beyond ours, then the universe as a whole contained more stars than anyone had imagined. The scale of the Milky Way was just the beginning. It opened the door to understanding cosmic structure on larger and larger scales. Galaxies clustered into groups. Groups formed superclusters, and superclusters stretched across hundreds of millions of light-years, forming a cosmic web that filled the observable universe. But even as the scale expanded outward, the immediate wonder remained focused on the Milky Way. Because this was home. This was where we lived, and understanding its size was the first step toward understanding our place within it. The question of how long it would take to cross the galaxy emerged naturally from this wonder. Once you know the scale, once you grasp that the galaxy is 100,000 light-years wide, the next thought is, could we ever cross it? How long would it take? And the answer, when calculated, was humbling. At light speed, 100,000 years. With our spacecraft, billions of years. The crossing, even for light, was measured in timescales that dwarfed human history. This was the first response. A mixture of wonder at the scale, humility at our smallness, and curiosity about what the scale meant for exploration. The galaxy was vast, but it was also ours, at least in the sense that we belonged to it. And belonging meant trying to understand it, even when understanding revealed distances we could never hope to cross. For those who first grasped the true size of the Milky Way, the emotional impact was profound. It wasn't just about numbers, it was about perspective. About realizing that the universe was far larger than the human mind was built to comprehend. And yet, that realization didn't diminish curiosity. If anything, it intensified it. The larger the galaxy appeared, the more questions arose. What lay in the distant arms? What happened near the center? How did the structure form? How would it evolve? The first response to scale was not to turn away, but to lean in, to measure more carefully, to observe more deeply, to map with greater precision. And that response continues today. Each new telescope, each new survey, each refinement of the measurements adds to the picture. The Milky Way is 100,000 light-years across. We know this with confidence now, built on a century of observations, but knowing the scale doesn't diminish the wonder. If anything, it deepens it. Because the more we learn about the galaxy's size, the more we appreciate the achievement of measuring it. The more we understand the distances, the more remarkable it seems that we can understand them at all. The first response to the discovery of the Milky Way's scale was awe. And awe, rather than being a stopping point, became a starting point, a foundation for deeper questions, more ambitious observations, and the slow accumulation of knowledge that allows us, tonight, to ask with precision, how long would it take to cross our galaxy? The answer begins with that first response, with the wonder at scale, with the humbling recognition that we are small but capable, tiny but curious, brief but able to measure timescales that stretch across hundreds of thousands of years. That recognition, that first response, is what allows the question to matter, because it roots the question not in fantasy, but in reality. We know the scale, we've measured it, and from that measurement we can calculate, we can compare, we can dream and wonder and imagine what it would mean to traverse the vast spiral we call home. The wonder persists. Every time a new image of the Milky Way is processed, every time Gaia releases more data, every time a telescope peers deeper into the disk, the scale is reaffirmed. 100,000 light-years, a span so vast that it resists comprehension. Yet we comprehend it anyway. We hold it in our minds, not as a visceral experience, but as a measured truth. And that truth, discovered through centuries of patient observation, is what transforms the question from idle speculation into something more. How long would it take to cross? The first response was wonder. The next response, which we'll explore as the night continues, is calculation. Taking that wonder and turning it into numbers, speeds, time spans, translating awe into understanding, but the wonder never fully leaves. It remains as the foundation, the reminder that even when we calculate precisely, even when we measure carefully, the galaxy remains vast beyond ordinary experience, a structure that demands both precision and poetry to truly grasp. When someone asks you how long it would take to cross the galaxy, they're expecting a single number, a clear answer. Days, years, millennia, whatever it is. But the truth is more complicated, because the answer depends entirely on what you mean by cross and what speed you're travelling. This is the central contradiction we must confront. The galaxy doesn't have one crossing time. It has many, each one valid, each one true, depending on your perspective. Let's start with the fastest possible answer. Light speed. 300,000 kilometers per second. At that ultimate velocity, the crossing takes 100,000 years. That's the baseline, the absolute minimum. Nothing can travel faster, so nothing can cross the galaxy quicker than that. But already, we see the problem. 100,000 years is not a timescale humans can experience. It's longer than our entire history as a species. So, even at the cosmic speed limit, the crossing is impossible for any individual. Now, slow down, way down, to the speeds we can actually achieve. Voyager 1, humanity's fastest and most distant probe, travels at about 61,000 kilometers per hour relative to the Sun. Sounds fast. And by human standards, it is. That spacecraft could cross the United States in less than 5 minutes. But against the scale of the galaxy, it's crawling. At Voyager's speed, the crossing would take approximately 1.5 billion years. 1.5 billion years? That's about 1/3 the age of Earth itself. The dinosaurs went extinct 65 million years ago. Multiply that span by more than 20, and you still haven't reached the time Voyager would need. What about faster spacecraft? The Parker Solar Probe, which dives close to the Sun and uses its gravity to accelerate, reaches speeds of about 700,000 kilometers per hour at its fastest. At that pace, the crossing shrinks to about 600 million years. Still impossibly long, still measured in timescales that exceed the age of complex life on Earth. These aren't theoretical numbers. These are actual spacecraft we've built. And they show the brutal reality. Our technology is nowhere near fast enough to make galactic crossings feasible. But let's imagine better engines. Nuclear propulsion, fusion drives, antimatter, technologies that exist, not on paper but not yet in practice. A fusion-powered ship might reach 10% of light speed. That's 30,000 kilometers per second, far faster than anything we've built. At that velocity, the crossing would take 1 million years. 1 million years. Homo sapiens has existed for maybe 300,000 years. Modern civilization is only about 10,000 years old. A million-year journey exceeds the entire timeline of our species. Push the speed higher, 20% of light speed. Now we're talking 50 years to reach the nearest star, Alpha Centauri. And the crossing of the galaxy drops to 500,000 years. Still impossibly long. Still beyond any conceivable human time frame. At half the speed of light, the crossing takes 200,000 years. At 90%, 111,000 years. Even approaching the cosmic limit, the journey spans epochs. Here's where the contradiction deepens. Because there's another way to measure time, not from Earth's perspective, but from the traveller's. Einstein's relativity tells us that time slows down for objects moving at very high speeds. The closer you get to light speed, the more time dilates. From the traveller's point of view, the journey becomes shorter. At 90% of light speed, time dilation means that what feels like 111,000 years to someone at rest might feel like only 48,000 years to the traveller. Still long, still impossibly long by human standards. But shorter. At 99% of light speed, the dilation becomes more extreme. The journey that takes 100,000 years from Earth's frame might feel like only 14,000 years to the crew. At 99.9%, it drops to about 4,500 years. And at 99.99%, the subjective time shrinks to around 1,400 years. Now we're in a range where, if you could somehow extend human lifespans or use generation ships, the crossing might be conceivable. Not for an individual, but for a society, for a chain of generations living and dying aboard a vessel. But here's the contradiction. While the traveller experiences a shorter time, the rest of the universe does not. Back on Earth, 100,000 years still pass, civilizations rise and fall, species evolve, the world changes beyond recognition. So, the crossing takes both 4,500 years and 100,000 years. Both answers are true, one from the traveller's perspective, one from the outside observer's. This is what makes the question so strange. There isn't one answer. There are multiple answers, each valid depending on your reference frame. From light's perspective, if photons could experience time, the crossing would be instantaneous. Zero time. They leave one side and arrive at the other with no duration between. From a traveller at 99% light speed, the crossing is a few thousand years. From Earth, watching that traveller, the crossing takes nearly 100,000 years. And from our current technology's perspective, moving at Voyager's pace, the crossing takes over 1 billion years. All of these are true simultaneously. The contradiction isn't a problem with the math. It's a feature of reality. Time and space are not absolute. They depend on motion. And when motion approaches light speed, the dependence becomes extreme. This multiplicity of answers is frustrating if you want a simple response. But it's also beautiful. It shows that the universe is richer than our everyday intuitions suggest. That time itself is flexible, dependent on perspective. For our purposes, trying to understand how long it would take to cross the galaxy, we have to accept that there is no single answer. We have to hold multiple truths at once. At light speed, 100,000 years. At realistic spacecraft speeds, hundreds of millions to billions of years. At speculative high speeds, with time dilation, thousands to tens of thousands of years subjectively, but still 100,000 externally. Each answer tells us something different, each one valid in its own context, and together they paint a picture of a galaxy that is vast beyond crossing, yet not entirely beyond imagination. The contradiction isn't a flaw in our understanding. It's a reflection of the complexity of space-time, of the interplay between speed and duration, of the challenge of measuring journeys that span cosmic scales. When we ask how long it would take to cross the galaxy, we're really asking multiple questions at once. How long for light? How long for us? How long from whose perspective? and each question yields a different answer. This is why the question is so compelling. It doesn't have a neat resolution. It opens into layers, each one revealing another aspect of the problem, another dimension of scale. As we continue through this night, we'll explore those layers more deeply. We'll look at what it would mean to travel at different speeds. We'll consider generation ships and time dilation. We'll dream of technologies that might close the gap. But we'll carry this contradiction with us. The recognition that the crossing has multiple durations, none more true than the others, all of them reflecting different perspectives on the same vast structure. The galaxy doesn't care about our definitions of time. It simply is 100,000 light-years wide, rotating slowly, filled with billions of stars. How long it takes to cross depends entirely on how fast you move and from whose clock you measure. And that contradiction, that multiplicity of valid answers, is part of what makes the question so endlessly fascinating. The contradiction remains unresolved because it cannot be resolved. There is no single truth here, only truths plural, each dependent on velocity and reference frame. And perhaps that's appropriate, because the galaxy itself defies singular description. It is a disk and a sphere, depending on whether you measure the visible stars or the dark matter halo. It is 100,000 light-years across, or 90,000, or 120,000, depending on how you define the edge. It contains between 200 billion and 400 billion stars, depending on how you count. Every measurement of the galaxy carries uncertainty, multiplicity, the recognition that cosmic structures resist simple answers. So too with the crossing time. It is 100,000 years. It is 1 billion years. It is 4,000 years subjectively. All true, all real, all valid windows into the same underlying question. And as we hold these contradictions gently, we begin to see that the question itself is more important than any single answer. The crossing time matters less than what it reveals, that we live in a structure so vast it bends our understanding of time itself. When scientists and dreamers contemplate crossing the galaxy, they approach the question from different angles. Each perspective yields different insights, different possibilities, different limits. Together, these theories paint a fuller picture than any single view could provide. The first theory is purely physical. It asks, what does physics allow? And the answer, grounded in Einstein's relativity, is clear. Nothing with mass can reach or exceed the speed of light. That's not a technological limit. It's a fundamental law. At light speed, the galaxy takes 100,000 years to cross. That's the floor, the absolute minimum. No technology, no matter how advanced, can reduce that time by travelling faster through space. This physical theory establishes the boundary. Everything else must work within it. The second theory is engineering-focused. It asks, what can we actually build? And here, the answers are far less optimistic. Our fastest spacecraft, Voyager 1, moves at a tiny fraction of light speed, about 0.006% to be precise. At that pace, crossing takes over 1 billion years. Even our most ambitious propulsion concepts, fusion drives or antimatter engines, might reach 10 to 20% of light speed. That shrinks the crossing to hundreds of thousands of years, better than billions, but still impossibly long. Engineering theory tells us that even our dreams, when grounded in chemistry and physics we understand, fall far short of making galactic crossings practical. The third theory is biological. It asks, what about generation ships? If no individual can make the journey, perhaps a society can. Imagine a vessel large enough to support thousands of people, self-sustaining, with agriculture, recycling, energy production, a miniature world that could last for millennia. Launch it at 10% light speed toward the far side of the galaxy. The crossing takes 1 million years, divided by human generations of about 25 years each. That's 40,000 generations. 40,000 generations. The entire span from the first humans to today is only about 10,000 generations. Can we imagine a society maintaining purpose, coherence, and genetic diversity for 40,000 generations aboard a ship? The biological theory suggests it's possible, in principle, but it raises profound questions about identity, culture, and continuity. Would the descendants even remember why they were travelling? The fourth theory is psychological. It focuses on isolation. Crossing the galaxy means leaving everything behind, not just Earth, but all contact with it. At even moderate speeds, communication becomes impossible. A message sent from halfway across the galaxy would take 50,000 years to arrive. There's no conversation possible across such spans, no updates, no guidance, no reassurance that anyone remembers you exist. The psychological theory asks, can humans endure that level of isolation? And if not, does that render the crossing impossible regardless of technology? The fifth theory is relativistic. It embraces time dilation as a tool. If a ship travels at 99.9% light speed, the subjective journey time drops dramatically. What takes 100,000 years from Earth's perspective might feel like only a few thousand years to the crew. This relativistic theory offers hope. It suggests that with sufficient speed, the crossing becomes conceivable within a civilization's lifetime, if not an individual's. But it comes with a cost. The travellers would be exiled not just in space, but in time. They'd leave one era and arrive in another, with everything they knew long vanished. The sixth theory is cosmological. It asks, what about the galaxy's motion? The Milky Way doesn't sit still. It moves through space, pulled by the gravity of other galaxies. Part of the local group that includes Andromeda and dozens of smaller galaxies. If you're crossing the galaxy, you're not just moving through a static structure, you're navigating something in motion, rotating, evolving. The stars you aim for will have moved by the time you arrive. Cosmological theory adds complexity to the crossing. It's not a straight line through fixed space, but a trajectory through a dynamic system. The seventh theory is energetic. It calculates the energy requirements of different speeds. To accelerate even a small ship to a significant fraction of light speed requires enormous energy. To accelerate a large generation ship requires even more. Where does that energy come from? Chemical rockets can't provide it. Nuclear reactions might. Antimatter theoretically could, but we don't know how to produce or store it in useful quantities. Energetic theory suggests that the crossing is limited not by physics or engineering alone, but by energy availability. Without abundant, concentrated power sources, high speeds remain out of reach. The eighth theory is practical. It asks, why cross at all? Perhaps the goal isn't to traverse a galaxy, but to explore it locally, spreading from star to star in waves rather than long jumps. A civilization could send probes or colony ships to nearby stars. Those colonies could then send ships farther out. Over millions of years, the wave of exploration could cover significant portions of the galaxy without any single journey being impossibly long. Practical theory trades the romantic notion of a direct crossing for the patience of incremental expansion. It accepts that the galaxy won't be crossed in one leap, but might be filled over time. The ninth theory is speculative. It imagines technologies we don't yet understand. Wormholes that connect distant points, warp drives that compress space, manipulation of higher dimensions, quantum shortcuts. None of these exist. Some may be impossible, but they represent the outer edge of imagination, the places where theory meets hope, where established physics gives way to speculation about what might be possible with knowledge don't yet have. Speculative theory doesn't provide answers so much as questions. It asks, what if? And in asking, it keeps the dream alive even when practical calculations seem discouraging. Each of these theories, each perspective, offers something valuable. The physical theory sets the limits. The engineering theory grounds us in reality. The biological theory explores social possibilities. The psychological theory confronts human nature. The relativistic theory uses Einstein's equations to offer hope. The cosmological theory adds complexity. The energetic theory identifies bottlenecks. The practical theory suggests patience. And the speculative theory dreams. Together, they form a framework for thinking about the crossing. Not a single path, but a landscape of possibilities, each with its own constraints and opportunities. When we ask how long it would take to cross the galaxy, the answer depends on which theory we prioritize. If we focus on physics, the answer is 100,000 years minimum. If we focus on current engineering, it's billions of years. If we embrace time dilation, it might be thousands of years subjectively. If we imagine wormholes, it could be instantaneous. The theories don't contradict each other so much as layer upon each other, each adding depth to our understanding. And together, they reveal that crossing the galaxy is not a simple engineering challenge. It's a multifaceted problem touching on physics, biology, psychology, energy, and imagination. As we continue through this night, we'll explore some of these theories more deeply. We'll calculate journey times. We'll imagine generation ships. We'll ponder time dilation's strange gift. We'll dream of shortcuts and confront limitations. But we'll carry with us this recognition that the question of crossing the galaxy admits multiple perspectives, multiple theories, multiple valid approaches, and that the richness of the question lies not in finding one answer, but in exploring the space of possibilities these theories create. The theories continue to multiply as our knowledge deepens. String theory suggests 11 dimensions, most of them curled too small to perceive. Could some of those dimensions offer shortcuts? Dark energy makes up most of the universe's content, yet we barely understand it. Could it be harnessed for propulsion? Quantum entanglement connects particles across arbitrary distances instantaneously. Could that principle somehow be scaled? These questions sit at the frontier, where established science meets speculation, where theories become increasingly tentative, but no less important for exploration. They show that even when faced with seemingly insurmountable barriers, human imagination continues to probe for possibilities, to ask what might lie beyond current understanding. The theories we hold today about crossing the galaxy will surely evolve. New discoveries in physics may open paths we cannot yet conceive, or they may close doors we currently imagine are open. But the act of theorizing itself, of approaching the problem from every angle we can think of, is how we transform an impossible question into one that at least has the shape of potential answers, even if those answers remain distant. In 1977, humanity launched 2 spacecraft that would become the most distant objects we've ever sent into space. They were called Voyager 1 and Voyager 2, and they were built to explore the outer planets, Jupiter and Saturn, Uranus and Neptune. But their missions didn't end when those encounters were complete. They kept going, and they're still going now, more than 45 years later, drifting outward into the space between stars. These 2 probes, primitive by modern standards, built with technology from the 1970s, have become our investigation into what it means to leave home. They're the closest we've come to attempting a crossing, even though they'll never reach another star system in any time frame we can imagine. Voyager 1 launched on September 5th, 1977. Its twin, Voyager 2, actually launched earlier, on August 20th, but followed a slower trajectory. Together, they took advantage of a rare alignment of the outer planets, a configuration that occurs only once every 176 years. This alignment allowed them to use gravity assists, swinging past one planet to gain speed for the next. Jupiter's immense gravity accelerated Voyager 1, flinging it towards Saturn. Saturn's gravity redirected it upward, out of the plane of the planets, on a path toward interstellar space. Voyager 2 followed a different route, visiting all 4 giant planets before heading outward. The encounters transformed our understanding. Jupiter revealed its intricate cloud bands, its great red spot, and active volcanoes on its moon Io. Saturn showed its ring system in unprecedented detail, with thousands of individual ringlets shaped by gravity. Uranus appeared as a tilted, featureless world, its moons showing surprising diversity. And Neptune, the final stop, displayed violent storms and a moon, Triton, with geysers erupting from its frozen surface. Each flyby was a revelation, but for our purposes tonight, what matters most is what happened after. After the planetary encounters ended, after the cameras were turned off to save power, After the primary missions were declared complete, the Voyagers kept travelling. Today, Voyager 1 is more than 24 billion kilometres from Earth. That's about 160 astronomical units, where one astronomical unit is the distance from Earth to the Sun. In more familiar terms, it's roughly 14 times farther from the Sun than Pluto. Voyager 2 is slightly closer, at about 20 billion kilometres, or 134 astronomical units. Both have crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium. They're the first human-made objects to enter interstellar space. Though they're still within the Sun's gravitational influence and will be for tens of thousands of years. At their current speeds, approximately 61,000 km per hour for Voyager 1 and 55,000 km per hour for Voyager 2, neither will ever reach another star. Not in human timeframes. Not in timeframes we can even conceptually grasp. Voyager 1 is heading roughly toward a star called Gliese 445. In about 40,000 years, it will pass within 1.6 light-years of that star, close on galactic scales, but still not an encounter, just a passing, silent and unnoticed. Voyager 2 is aimed toward a star called Ross 248. It will approach it in about 40,000 years as well, passing within about 1.7 light-years. These are the nearest approaches either spacecraft will make to another star, and both are still farther from those stars than the distance from our Sun to the nearest star system, Alpha Centauri. But let's consider what the Voyagers tell us about crossing the galaxy. At Voyager 1's current speed, travelling constantly without slowing, it would take approximately 1.5 billion years to traverse the Milky Way's 100,000 light-year width. 1.5 billion years. To put that in perspective, Earth is about 4.5 billion years old. The earliest life appeared about 3.8 billion years ago. Complex multicellular life emerged only about 600 million years ago. A journey equal to 1.5 billion years would span more than twice the entire history of complex life on our planet. The Voyagers were never meant to cross the galaxy. They were designed to explore the outer solar system, a mission they completed brilliantly. But their continued journey outward gives us a tangible reference point for understanding galactic scale. These are real machines, built by humans, launched from Earth, travelling through space right now, and even at their velocity, which seems fast to us, the galaxy remains impossibly distant. Each Voyager carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth. Music from Bach, Beethoven, Chuck Berry, and traditional songs from around the world. Greetings in 55 languages. Natural sounds, thunder, wind, waves, birdsong, and 116 images depicting life on Earth. The records were curated by a team led by Carl Sagan. They're not practical communication devices. The odds of another civilization finding a Voyager and deciphering the record are vanishingly small, but they're symbolic. They say that we were here, that we reached out, that we cared about being remembered, even if the memory outlasts us by billions of years. The Voyagers will continue drifting long after they fall silent. Their power supplies, radioisotope thermoelectric generators using decaying plutonium, will produce less electricity each year. Eventually, probably sometime in the 2020s or early 2030s, there won't be enough power to run even the most essential systems. When that happens, the Voyagers will go silent, but they won't stop moving. They'll continue on their trajectories, cold and dark, for millions or billions of years. In a way, they'll outlast almost everything we build on Earth. Cities will crumble, languages will change beyond recognition, species will evolve, continents will shift, and the Voyagers will still be travelling, unchanged except by the occasional impact of dust, carrying their golden records through the interstellar void. What do the Voyagers teach us about crossing the galaxy? Several things, all of them humbling. First, they show us that human-made objects can survive in space for decades. This wasn't guaranteed. The environment is harsh, radiation, extreme cold, micrometeorite impacts. But the voyages endure, a testament to careful engineering. Second, they demonstrate that we can maintain communication across vast distances. The signals from Voyager 1 take more than 22 hours to reach Earth, travelling at the speed of light. Yet we can still receive them, still decode them, still extract information from transmissions so faint they arrive with less power than it takes to light a single LED. This tells us that if we ever do send probes across the galaxy, communication is possible in principle, even if the delays make conversation impossible. Third, they reveal the limitations of chemical propulsion. The Voyagers gain their speed partly from rocket burns, but mostly from gravity assists. They use the planets as stepping stones, stealing a fraction of each world's orbital momentum. Without those assists, they'd be moving much slower. And even with them, their velocity is tiny compared to what would be needed for galactic travel. Fourth, they give us a baseline for comparison. When we talk about crossing, times measured in billions of years, it's helpful to have a real example. The Voyagers aren't hypothetical. They're out there, right now, moving at speeds we've actually achieved. And at those speeds, the galaxy remains forever out of reach. But perhaps most importantly, the Voyagers remind us that exploration is not always about reaching a destination. Sometimes, the journey itself matters. The act of reaching outward, of sending something beyond our immediate neighbourhood, of declaring our existence to the cosmos. The Voyagers will never cross the galaxy. They'll never reach the speeds necessary to make even a single crossing of the distance to another star system in reasonable time. But they've crossed the heliopause. They've entered interstellar space. And in doing so, they've shown us what's possible, even if what's possible falls far short of what we might dream. For the investigation of galactic crossing times, the Voyagers serve as our ground truth. They're the fastest machines we've sent on outbound trajectories, and they show us, clearly and undeniably, that with our current technology, crossing the galaxy isn't just difficult, it's effectively impossible. 1.5 billion years is not a journey. It's a geological epoch. It's longer than the time since life moved from single cells to complex organisms. It's a span so vast that by the time the crossing completed, Earth itself might be unrecognizable. And yet, the Voyagers persist. Every day, they travel farther from home. Every hour, they cover another 60,000 kilometers. The distance accumulates, slowly but steadily. In that persistence, there's something worth noting. The Voyagers don't rush. They can't. They simply move at their constant velocity, indifferent to the vastness ahead. They're patient travellers, even though their patience will never be rewarded with arrival. Perhaps that's the lesson they offer, that the investigation of cosmic distances requires patience beyond a human scale, that exploring the galaxy is not a sprint or even a marathon, but a relay spanning millions or billions of years. The Voyagers are our first runners in that relay. They won't complete the race, they won't even complete the first leg, but they've started. They've shown it's possible to leave, even if reaching the destination remains beyond us. As we think about crossing the galaxy, as we calculate times and speeds and compare technologies, the Voyagers ground us. They remind us where we actually are, what we've actually achieved, and how far we have yet to go. They're still out there, drifting in the darkness between stars, carrying humanity's message on golden discs, not crossing the galaxy, but pointing the way. Silent investigators moving through space at 1/61,000th the speed of light, taking 1.5 billion years to make a journey that light completes in 100,000. That ratio, that vast gulf between what we can do and what would be needed, is the investigation's most important finding. The Voyagers show us the distance we must travel, not just in space, but in capability, before galactic crossings move from impossible to merely inconceivable. And as they drift farther into the dark, they carry with them our hopes, our curiosity, and our determination to reach beyond our limits, even when those limits seem insurmountable. If we want to understand how long it would take to cross the galaxy, we need a benchmark, a standard against which all other speeds can be measured. And in the universe, there's only one ultimate standard, the speed of light. Light moves at 299,000 792 kilometers per second in vacuum, usually rounded to 300,000 kilometers per second for simplicity. This is not just fast. It's the cosmic speed limit, the fastest anything can travel through space. The speed of light, often written as c in equations, is special. It's the same for all observers, regardless of their motion. It's woven into the structure of space-time itself, and it sets the absolute floor on how long any journey can take. For crossing the Milky Way, the data is straightforward. The galaxy is approximately 100,000 light-years wide. Light, by definition, takes 100,000 years to cover that distance. This is our benchmark. 100,000 years. Nothing can cross the galaxy faster than that. Not because we lack the technology, but because the laws of physics forbid it. Let's break down what this means. A photon leaving one edge of the galactic disk will arrive at the other edge 100,000 years later. Assuming it travels in a straight line and nothing absorbs it along the way, during those 100,000 years, many things happen. Stars are born and die, planets form, civilizations could rise and fall multiple times over, entire epochs of history could unfold. But for the photon, travelling at light speed, time does not pass. This is one of relativity's strange gifts. At the speed of light, time stops. The photon experiences no duration between emission and absorption. From its perspective, if it had one, the journey is instantaneous. This creates an interesting contrast. From our perspective, watching from a distance, the crossing takes 100,000 years. From light's perspective, it takes zero time. Both statements are true. They simply reflect different reference frames. The speed of light was first measured with reasonable accuracy in the late 17th century by Ole Rømer, who noticed that the timing of Jupiter's moon eclipses changed depending on Earth's position in its orbit. The light from Jupiter took longer to reach Earth when we were farther away. Later measurements refined the value. By the 20th century, we knew the speed of light to extraordinary precision, and with Einstein's relativity, we understood that it wasn't just a speed limit for light itself, but for everything. The data on light speed is among the most precisely measured quantities in physics. We know it to within a fraction of a meter per second, and that precision allows us to calculate galactic crossing times with confidence. 100,000 light-years equals approximately 946 trillion kilometers. That's the distance light covers in 100,000 years. No matter how you measure it, no matter what units you use, the relationship holds. Now let's compare light to other speeds we're more familiar with. Sound travels at about 1,235 kilometers per hour in air at sea level. Light travels about 880,000 times faster than that. A passenger jet cruises at about 900 kilometers per hour. Light is over 1 billion times faster. The fastest human spacecraft, the Parker Solar Probe, reaches about 700,000 kilometers per hour at its peak velocity near the Sun. Light travels about 1,500 times faster than that. Even our fastest probes are crawling compared to light. And light itself, for all its speed, still needs 100,000 years to cross the galaxy. The benchmark reveals the problem clearly. If the ultimate speed limit yields a crossing time measured in hundreds of centuries, then anything slower yields times measured in even more daunting spans. Divide light speed by 10 and you get a crossing time of 1 million years. Divide by 100 and it's 10 million years. Divide by 1,000 and it's 100 million years. The Voyager probes, travelling at about 161,000th the speed of light, need about 1.5 billion years. The data doesn't lie. The benchmark shows us exactly what we're up against. But light speed isn't just a barrier, it's also a tool. Every observation we make of the galaxy uses light. Visible light from stars, infrared radiation from dust clouds, radio waves from gas, X-rays from violent processes near black holes. All of these signals travel at light speed. When we observe the galactic centre, we're seeing light that left 27,000 years ago. When we observe distant arms of the spiral, we're seeing light from tens of thousands of years in the past. The galaxy as we know it is already a time machine. We never see it as it is now, but always as it was, with different regions viewed at different moments in their past. This has implications for crossing. If you sent a message from one side of the galaxy to the other, it would take 100,000 years to arrive. The sender would be long dead. The civilization that sent it might no longer exist, and any reply would take another 100,000 years to return. Communication across galactic distances, even at light speed, becomes a one-way transmission into the future rather than a conversation. The speed of light also determines what we can see. Light from the most distant parts of the galaxy has been travelling for tens of thousands of years. Anything farther than a certain distance is invisible to us, not because it's too faint, but because its light hasn't had time to reach us yet, given the age of the galaxy and our position within it. In a sense, light's finite speed means we're always looking at a galaxy that's slightly out of date. The map we've made is stitched together from observations at many different wavelengths, each showing the galaxy at different moments in its past. The benchmark of light speed also appears in other contexts. When planning missions to nearby stars, engineers calculate travel times based on fractions of light speed: 10% of c, 20%, 50%. Each fraction yields a different journey duration. But even these aspirational speeds, which we haven't achieved and don't know how to achieve, still leave galactic crossings in the realm of the impossible. At 10% of light speed, which would be an astonishing technological achievement, crossing the galaxy takes 1 million years. At 50%, it's 200,000 years. At 90%, it's 111,000 years. Only as you approach light speed very closely do the times drop toward the benchmark. At 99%, it's 101,000 years. At 99.9%, it's 100,000 and 100 years. The benchmark is stubborn. It yields only slightly, even to speeds that seem impossibly fast by human standards. This data, this precise measurement of light's velocity and the distances it must traverse, is what turns the question of crossing the galaxy from philosophical to mathematical. We can calculate exactly how long it would take at any given speed. And those calculations, grounded in the benchmark, show us the harsh reality. The galaxy is vast. Light is fast. But even light needs epochs to cross the distance. For humans, bound by mass and limited by engineering, the benchmark feels almost cruel. It shows us that even the universe's ultimate speed limit isn't enough to make galactic crossings practical. But the benchmark also provides clarity. It tells us what we're aiming for, even if we can never quite reach it. It gives us a standard to measure against, and it reminds us that some limits are not imposed by technology, but by the fundamental structure of reality itself. Light speed is not just fast, it's the fastest. And 100,000 years at that ultimate velocity is the absolute floor for crossing the Milky Way. Every other speed, every real spacecraft, every imagined propulsion system must be slower, and slower means longer. The benchmark is the best case. Everything else falls short. As we continue through this night, as we explore different approaches to the crossing, we'll carry this benchmark with us. 100,000 years at light speed. That's the data. That's the truth. And it shapes every other calculation we make. The speed of light is not negotiable. It's written into the equations that govern space-time. And those equations, for all their elegance and precision, offer no shortcuts. The crossing takes 100,000 years at minimum. That's the data. And the data is unforgiving. The benchmark reminds us that the universe operates on scales we didn't evolve to comprehend. We evolved to chase prey across savannas, to throw stones at targets, to navigate forests and rivers. Our intuitions about speed and distance are built for those contexts. But light speed, and the distances it must traverse to cross a galaxy, exist in a different realm entirely. A realm where intuition fails and only mathematics guides us. The data from light speed measurements, refined over centuries, now precise to within meters per second, gives us that mathematical foundation. It tells us exactly what the universe allows and what it forbids. And what it allows, barely, is a crossing in 100,000 years if you could somehow travel as fast as the universe permits. What it forbids is anything faster. The benchmark stands immovable, a line in the fabric of space-time itself, reminding us that some barriers are not technological but fundamental, written into the deepest laws of nature. Hidden within Einstein's equations is something strange, something that seems to offer a loophole, a way around the harsh verdict that crossing the galaxy takes forever. It's called time dilation, and it reveals that time itself is not absolute. It depends on how fast you're moving. This is the deeper mystery, the realization that if you could somehow travel very fast, approaching the speed of light, the journey across the galaxy might feel shorter for you, even though it still takes 100,000 years from everyone else's perspective. The mathematics is straightforward, but the implications are profound. As an object approaches light speed, time slows down for it relative to stationary observers. This isn't an illusion or a trick. It's a real physical effect, confirmed by countless experiments. Atomic clocks flown on aircraft tick slightly slower than identical clocks left on the ground. Particles accelerated to near light speed in colliders live longer than they should before decaying. GPS satellites must correct for time dilation, or their positioning data would drift. Time dilation is real, and at speeds approaching light speed, it becomes extreme. Imagine a spacecraft accelerating to 90% of light speed. From Earth's perspective, the journey across the galaxy takes about 111,000 years. But aboard the ship, time runs slower. The crew would age less. Their clocks would tick less. From their perspective, subjectively, the journey might take only about 48,000 years. Still impossibly long by human standards, still far beyond any individual's lifetime. But less than half. What an outside observer measures. Push the speed higher. At 99% of light speed, time dilation becomes more pronounced. What takes 100,000 years externally might feel like only 14,000 years to the travellers. At 99.9%, it drops to about 4,500 years. At 99.99%, around 1,400 years, and as you approach light speed ever more closely, the subjective time continues to shrink. At 99.999%, the journey might feel like only a few hundred years. This is time dilation's gift. It offers the possibility that travellers moving very fast could experience the crossing in much less time than the universe measures. But the gift comes with conditions, and those conditions are severe. First, you need to reach those extraordinary speeds. 99.9% of light speed is far beyond anything we know how to achieve. The energy requirements are staggering. The engineering challenges are immense. The risks of collision with interstellar dust at such velocities are catastrophic. Second, time dilation doesn't reduce the time for the outside universe. From Earth's perspective, the crossing still takes 100,000 years. If you left today and sent a message back upon arrival, that message would return in 200,000 years. Anyone who watched you leave would be long dead. Their civilization might be gone. The language they spoke might be extinct. Everything familiar would have changed beyond recognition. Third, time dilation creates a profound isolation. You're not just travelling through space, you're travelling through time. You're leaving your own era and arriving in another. The travellers become exiles, separated from everything they knew by a gulf of time they didn't experience but everyone else did. This is the mystery. Time dilation offers a way to subjectively shorten the journey, but it does so by severing the connection to home. The price of the gift is disconnection. Einstein first described time dilation in 1905 as part of his special theory of relativity. The mathematics showed that time and space are not separate, but woven together into space-time. And that space-time has properties that seem strange to our everyday intuitions. One of those properties is that time runs at different rates depending on motion, not because of some mechanical effect, but because of the fundamental structure of the universe. The theory was tested and confirmed. Again and again, experiments showed that time dilation was real. Moving clocks do run slow, not by much at ordinary speeds, but measurably. and the effect grows more extreme as velocity increases. For galactic travel, time dilation offers theoretical hope. If a ship could reach 99.99% of light speed, a crew might subjectively experience the crossing in perhaps a few centuries rather than 100,000 years. That's still a generational voyage. An individual would complete it. But a society aboard a ship might. A culture could persist across a few centuries with careful planning. The mystery deepens when you consider that this isn't science fiction. It's physics. Time dilation is real, measured, understood. The equations are precise. The predictions are confirmed. What's missing is the engineering. We don't know how to accelerate massive spacecraft to such speeds. We don't know how to shield them from impacts. We don't know how to provide energy for such journeys or how to decelerate at the destination. But the physics allows it. That's the gift. The universe permits subjectively shorter crossings through time dilation. It just demands speeds we can't achieve. There's also a strange symmetry in time dilation. From the traveller's perspective, it's not their time that slows. It's the universe outside that speeds up. They experience their time as normal. But when they look back, they see Earth's clock racing ahead. Both perspectives are valid. Time is relative. There's no absolute frame. The traveller's reduced crossing time and Earth's 100,000-year wait are both true, just measured from different reference frames. This relativity is the deeper mystery. It challenges our intuition that time is universal, that everyone experiences duration the same way. Einstein showed that they don't, and at high speeds, the differences become impossible to ignore. For those dreaming of crossing the galaxy, time dilation offers something precious. The possibility, however distant, that the journey might be experienced in less than the age of civilizations, that a crew might depart and arrive within a time frame that could be remembered, recorded, understood. But it also highlights the cost. Even if the travellers experience only a few hundred years, they arrive in a galaxy where 100,000 years have passed. They're strangers in time. Everything they left behind is ancient history. The gift of time dilation is real. But it's a gift that comes with permanent exile, a way to shorten the journey for yourself while the rest of the universe moves on without you. This deeper mystery reveals something profound about the universe. That time is not a fixed backdrop against which events unfold, but a dynamic part of space-time that bends and flexes with motion and gravity. Crossing the galaxy forces us to confront this truth. Because at the speeds necessary to make time dilation matter, you're not just travelling, you're manipulating time itself, stretching and compressing it through your motion. The mystery isn't that time dilation makes galactic crossings easy. It doesn't. Even with its gift, the journey remains extraordinarily difficult. The mystery is that it makes them conceivable. That somewhere in the equations of relativity, there's a pathway where the crossing could be experienced in time frames that human societies might endure, even if we're nowhere close to walking that path. Time dilation is real, it's tested, it's understood, and it offers a strange kind of hope. Not that we can cross the galaxy quickly by any external measure, but that we might be able to experience the crossing in less time than it takes civilizations to rise and fall. That's the gift. And the mystery, and the strange comfort that physics, while imposing harsh limits, also offers occasional loopholes. Not to break the rules, but to use them in ways that seem almost designed to preserve possibility. As we move deeper into this night, as we explore what crossing might mean, we'll carry this mystery with us. Time dilation won't solve the problem, but it transforms it. It takes a journey that seems absolutely impossible and makes it merely inconceivably difficult. And in that transformation, there's a sliver of hope, narrow, distant, probably unreachable, but present, written into the structure of space-time itself, waiting for anyone who can achieve the speeds necessary to claim it. The mystery of time dilation also raises philosophical questions that go beyond physics. If you could travel at such speeds, would you? Would you leave behind everyone you know, everything familiar, to arrive in a future where you're the ancient one, the visitor from a vanished age? Some might say yes. The chance to see the galaxy, to witness the future, to participate in the longest journey imaginable might be worth the cost. Others would decline, unable to bear the thought of such permanent separation. Time dilation doesn't just offer a technical possibility, it offers a moral choice, a decision about whether the journey matters more than the connection to home. And perhaps that's the deepest mystery of all, not how time dilation works, but what it means to use it. To voluntarily step outside your own time, to trade the familiar for the unknown, to become a traveller not just through space but through the centuries, arriving in a world you'll never fully belong to. That choice, that profound existential decision, is time dilation's true gift and its heaviest burden. There comes a moment in any long exploration when you must stop calculating and start recognizing, when the numbers have all been crunched, the theories all examined, and you're left with a simple truth that can't be avoided. For the question of crossing the galaxy, that moment is now. The turning point where we acknowledge what all the data has been telling us. No human will ever cross the Milky Way in their lifetime. Not with current technology, not with any technology we can currently imagine. Not at speeds we know how to achieve or in time frames that fit within a human span. This is the reality. Not a temporary obstacle waiting for better engineering, but a fundamental confrontation with scale. The galaxy is 100,000 light-years wide. Light takes 100,000 years to cross it. Our fastest spacecraft need over 1 billion years. Even speculative fusion drives might reach speeds that reduce the crossing to hundreds of thousands of years. Still impossibly long, time dilation offers a loophole, but only at speeds so close to light that we have no idea how to achieve them. And even then, the subjective journey might take thousands of years, multiple human lifetimes, generations. The turning point is accepting that the galaxy is too vast, that our technologies, for all their advancement, are insufficient, that the distances involved are not just large but categorically different from anything we're equipped to handle. This recognition isn't defeat, it's clarity. It's the difference between wishful thinking and honest assessment. For centuries, humans dreamed of flying, and eventually we succeeded. For decades, we dreamed of reaching the moon. And we did. For years, we've dreamed of visiting Mars. And we likely will. But crossing the galaxy is not like those dreams. It's not a matter of better rockets or more funding or political will. It's a matter of confronting distances that remain vast even when measured at the universe's ultimate speed limit. The turning point asks us to let go of certain fantasies, to acknowledge that some things are beyond us, at least for now, probably forever. But the recognition also opens new perspectives. If we can't cross the galaxy as individuals, what can we do? We can explore locally, we can send probes to nearby stars, we can map the galaxy from where we are, we can understand its structure, its history, its place in the universe. We can appreciate that we live within something vast, that our home is not just Earth, not just the solar system, but the entire Milky Way, and that being part of something too large to cross doesn't diminish us, it situates us. The turning point is also historical. There have been other moments when humanity confronted its limits. When Copernicus showed we weren't at the centre of the solar system. When Shapley showed we weren't at the centre of the galaxy. When Hubble showed our galaxy was one of billions. Each time, the recognition was humbling. We were smaller, less central, less special than we thought. But each time, the recognition also brought deeper understanding. We saw ourselves more accurately. We understood our place more clearly. This is another such moment. Recognizing that we can't cross the galaxy is not admitting failure. It's understanding scale. It's acknowledging that the universe is larger than us, that its structures extend beyond our reach, and that our significance lies not in conquering distance but in comprehending it. The turning point changes the question. Instead of asking, how long would it take to cross the galaxy, we begin asking, what does it mean to live in a galaxy we cannot cross? And that question has richer answers. It means we're embedded in a structure that extends in time and space beyond our individual lives. It means our perspective is limited but real. It means we can know without reaching, understand without touching, appreciate without possessing. The recognition also affects how we think about the future. If galactic crossings are impossible, what about smaller steps? Can we send probes to nearby stars? Can we establish colonies within a few dozen light years? Can we create a network of human presence that gradually expands, not crossing the galaxy in one leap but spreading through it slowly over millions of years? These questions become more relevant once we accept the turning point. Once we stop fixating on the impossible and start considering the merely extraordinarily difficult. The turning point doesn't mean abandoning curiosity, it means redirecting it. Instead of asking how to cross, we ask how to explore, how to observe, how to understand from where we are. And from where we are, we can understand quite a lot. We've mapped the spiral structure. We've measured distances to thousands of stars. We've detected planets around other suns. We've observed the galactic center, traced the motion of stars orbiting the central black hole, studied star formation in distant nebulae. All of this without leaving our solar system, without crossing even a fraction of a light year. The recognition that we can't cross the galaxy doesn't limit what we can know, it only limits where we can go. And perhaps that's okay. Perhaps knowing is enough. Perhaps understanding the galaxy's structure, appreciating its scale, and recognizing our place within it is a sufficient achievement. The turning point is also personal. For anyone who's dreamed of galactic exploration, who's imagined visiting distant stars, who's hoped that humanity might one day spread across the Milky Way, the recognition is bittersweet. The dream doesn't die, but it transforms. It becomes less about individual journeys and more about long-term processes, less about destinations and more about trajectories, less about arrival and more about direction. We may never cross the galaxy, but we've started moving outward. Voyager 1 and 2 drift into interstellar space. Future probes may reach nearby stars within centuries. Slowly, incrementally, we extend our reach. The turning point acknowledges that this is enough, that the galaxy doesn't need to be crossed to be explored. That distances too vast for individual travel can still be bridged by knowledge, by light, by patient observation. There's wisdom in this recognition, a kind of peace that comes from accepting limits. Not every horizon is meant to be reached. Some are meant to be seen, appreciated, and left in place as reminders of how vast the universe is and how small we are within it. The turning point is where ambition meets reality, where dreams encounter physics, where hope adjusts to possibility. And in that adjustment, something valuable emerges, a clearer understanding of what we can do, a realistic assessment of challenges, and a deeper appreciation for what we've already achieved. We live in a galaxy too large to cross, but we've measured it, we've mapped it, we've understood its age, its structure, its evolution. We've done all of this from one small planet orbiting one ordinary star. That achievement, that capacity to know beyond our reach, is profound. It may not satisfy the dream of galactic exploration, but it satisfies the deeper human need to understand, to place ourselves in context, to know where we are and what surrounds us. The turning point is recognition, clear-eyed and honest. The galaxy is too vast, the distances too great, the speeds required too far beyond our capability. We won't cross it, not in our lifetimes, not in any time frame that connects to human experience. And acknowledging that truth is not resignation, it's the beginning of wisdom, the foundation for asking better questions, the pathway to appreciating what we have rather than mourning what we cannot reach. The turning point is where we stop measuring the impossible and start measuring ourselves, not by what we can achieve, but by what we can comprehend. Not by where we can travel, but by what we can know. And in that shift, in that recognition that some distances are too vast even for light to make them feel small, we find a different kind of achievement. We become not travellers of the galaxy, but students of it. Not conquerors of distance, but appreciators of scale. The turning point transforms the question from how long to cross to what does it mean that we cannot. And in that transformation, we discover that knowing the galaxy is too large to cross is itself a form of knowledge worth having, a truth that situates us properly in a universe that cares nothing for our limitations, but reveals them with perfect clarity through the simple, stubborn fact of distance. The galaxy is 100,000 light-years wide, and we are here, small and brief, looking outward with minds capable of measuring what we cannot traverse. That is the turning point. That is the recognition. And from here, we continue, not with dreams of crossing, but with the quieter satisfaction of understanding. Once we recognize that no individual can cross the galaxy, the question transforms. If the journey takes hundreds of thousands of years at best, millions or billions at our current speeds, then perhaps the answer isn't faster ships. Perhaps the answer is longer lives, not individual lives, but collective ones. Civilizations that persist across the centuries, passing the mission from generation to generation like a torch that never extinguishes. This is where the concept of generation ships emerges, not as a solution to the problem of distance, but as a response to it. A way of thinking about journeys that span timescales beyond any single lifetime. Imagine a vessel large enough to be a world unto itself. Kilometers long, perhaps, rotating to provide artificial gravity, containing farms, forests, water systems, living spaces for thousands or tens of thousands of people. This ship would need to be entirely self-sustaining. It couldn't rely on resupply from Earth. Once launched, it would be on its own for the entire journey. Air would need to be recycled, water reclaimed and purified, food grown in hydroponic gardens or enclosed biomes. Energy would come from nuclear reactors, perhaps fusion if we ever master it, or from vast arrays of solar panels, though as the ship moved farther from any star, solar power would become impractical. The population would need to be large enough to maintain genetic diversity. Too few people, and inbreeding becomes inevitable. Too many, and the resource demands become overwhelming. Estimates suggest a minimum of several thousand individuals, perhaps 10,000 or more to be safe. These people would live their entire lives aboard the ship. They would be born in its corridors. They would grow up seeing walls instead of horizons. They would work, fall in love, raise children, grow old, and die without ever setting foot on a planet. And crucially, they would never see the destination. Not the generation that launched, not their children, not their grandchildren, not for dozens or hundreds or thousands of generations. Let's do the mathematics. Suppose we could build a ship capable of reaching 10% of the speed of light. That would be a monumental achievement, far beyond anything we can currently do. But it's not prohibited by physics, just by engineering. At 10% of light speed, crossing 100,000 light-years takes 1 million years. A human generation is roughly 25 years. That's the average span from one generation having children to those children having their own. 1 million years divided by 25 years per generation equals 40,000 generations. 40,000 generations would need to live and die aboard that ship before reaching the far side of the galaxy. To put that in perspective, from the first anatomically modern humans to the present is only about 10,000 generations. All of recorded history, from the first written languages to now, is roughly 200 generations. A generation ship crossing the galaxy would need to persist for 40 times longer than humans have existed as a species. 200 times longer than all of civilization. Can we even imagine a society maintaining continuity across such spans? What would hold them together? What would keep the mission alive after the original purpose faded from living memory into ancient history into myth? These questions define the consequence of generational thinking. If crossing the galaxy requires generations, then it also requires rethinking what a society is, what holds it together, what gives it purpose across timescales no human culture has ever faced. Consider the challenges. First, governance. How would such a society be organized? Democracy might work for the first few generations, but over centuries, systems evolve. Would the ship eventually develop its own culture, its own religion, its own political structures, completely unlike anything Earth has known? Second, knowledge preservation. The mission's purpose must be maintained, but how do you ensure that Generation 500 remembers why Generation 1 launched? How do you prevent the story from becoming distorted, mythologized, or forgotten entirely? Some have suggested embedding the mission into every aspect of culture, making it the foundation of education, religion, art, creating rituals that reinforce the purpose, building monuments that cannot be ignored. But even with such efforts, drift seems inevitable. Languages change, cultural values shift. What seems urgent to one generation becomes quaint to another. Could any human society truly maintain focus on a goal that lies thousands of generations in the future? Third, genetic health. 10,000 people might provide enough diversity for a few centuries, but over millennia, even with careful genetic management, the population would begin to experience problems. Genetic bottlenecks, accumulation of harmful mutations, reduced fitness. Some proposals suggest freezing genetic material, creating a library of DNA from Earth that could be reintroduced to the population periodically. But this assumes technology that remains functional for hundreds of thousands of years. Fourth, psychological sustainability. Humans evolved in open environments with horizons. Being confined to a ship, no matter how large, for your entire life creates stresses we don't fully understand. The early generations might cope, sustained by the romance of the mission. But after dozens of generations, when everyone has only ever known the ship, when Earth is not even a memory but a story, would mental health problems become endemic? Would the population develop new psychological adaptations? Would they evolve, culturally or even biologically, into something different from baseline humanity? Fifth, technical maintenance. The ship must function flawlessly for the entire journey. Every system, every component, must be maintained, repaired, or replaced as needed. This requires not just mechanics, but knowledge. The descendants must understand the ship's systems well enough to keep them running. They must preserve technical manuals, training programs, expertise. But knowledge degrades. Texts are lost. Expertise is forgotten. Skills disappear when generations stop practicing them. How do you ensure that Generation 30,000 still knows how to repair a fusion reactor that won't fail for another 10,000 generations? These consequences flow directly from the recognition that individuals cannot cross the galaxy. If the journey requires more time than any human possesses, then the only option is to make the journey collective. But collective journeys have properties individual ones don't. They require institutions that outlast people. They require purpose that transcends personal motivation. They require planning on timescales that dwarf anything humans have ever attempted. The generation ship is a thought experiment in its purest form. It asks, could a human society persist for 40,000 generations with a single purpose? Could knowledge, culture, and motivation survive such spans? History offers few encouraging examples. The longest-lasting human institutions, certain religious traditions, or the concept of hereditary monarchy, have persisted for a few hundred generations at most, and even those have changed beyond recognition over such time spans. A generation ship would need to exceed all previous human achievements in continuity by factors of hundreds, and it would need to do so while physically isolated, unable to draw on fresh ideas or resources from a parent civilization. Some theorists suggest that artificial intelligence might help. An AI overseer could maintain perfect memory, preserve technical knowledge, and provide continuity across generations. It could serve as the ship's institutional memory, unchanging, while the human population evolves. But this creates new problems. Would humans eventually come to resent or worship the AI? Would they remain in control, or would the AI become the de facto ruler? And could any AI remain stable and functional for hundreds of thousands of years without developing its own goals, its own drift? The consequence of generational thinking is profound. It transforms the crossing from an engineering problem into a social one, from a question of speed and propulsion into a question of governance, culture, and meaning. And it reveals something fundamental about the galaxy's scale. The distances aren't just large. They're large enough to require rethinking what human society can be, what it can sustain, what purposes it can maintain. A generation ship is not just a vessel. It's a civilization, a mobile culture that must persist longer than any civilization has persisted on Earth. And the consequence of that requirement is humbling. Perhaps generation ships are possible. Perhaps with careful design, strong institutions, and determination, humans could build societies that endure for 40,000 generations. But the more likely consequence is recognizing that even this approach, creative as it is, still falls short. Because the distances are so vast that even extending our timescale from individuals to civilizations barely helps. The galaxy doesn't care about our timescales. It measures in light years and eons, and whether we think as individuals or as generations, the chasm remains. The consequence of accepting that crossing requires generations is not hope, exactly. It's a different kind of realism, an acknowledgement that if the galaxy is to be explored at all, it will require reimagining everything we mean by journey, society, and purpose. And even then, it might not be enough. There's beauty in the concept, though. The idea that humans might create something that outlasts them, that a society could persist across timescales that dwarf any individual life. That purpose could be maintained not through personal ambition but through collective commitment, passed down like fire from torch to torch. Generation ships represent perhaps the most profound expression of human hope. The belief that we can think beyond ourselves, plan for descendants we'll never meet, create institutions that serve people who won't exist for thousands of years. It's an expression of faith in continuity, in the value of distant goals, in the meaning of journeys that span epochs. And even if generation ships remain forever in the realm of thought experiments, the fact that we can conceive them, that we can imagine societies persisting across 40,000 generations, tells us something important about ourselves. We can think on scales that exceed our grasp. We can plan for futures we'll never see. And in that capacity, there's a kind of crossing already happening, not through space, but through time, not of the galaxy, but of the centuries. Understanding the true scale of the galaxy, accepting that we cannot cross it in any human time frame, has an impact that reaches far beyond astronomy. It reshapes how we think about exploration, about our place in the universe, about what dreams are worth pursuing. This impact is subtle at first. When you learn that the Milky Way is 100,000 light-years across, it's just a number. When you learn that even light takes 100,000 years to make the crossing, it becomes more real. And when you truly internalize that our fastest spacecraft would need over 1 billion years, that even speculative technologies might require hundreds of thousands of years, something shifts. The dream of exploring the galaxy doesn't die, but it transforms. It becomes less about going there and more about understanding from here, less about physical journeys and more about intellectual ones. This transformation has already begun. For most of human history, exploration meant travel. If you wanted to know what lay beyond the horizon, you had to go there, build a ship, cross the ocean, climb the mountain, trek through the wilderness. But with astronomy, we've discovered a different kind of exploration. We can study distant objects without visiting them. We can understand stars by analysing their light. We can map the galaxy by measuring positions and velocities. We can peer into the past by observing light that's been travelling for thousands of years. This is exploration by observation, and it's allowed us to know far more than physical travel ever could. We understand the structure of the Milky Way better than ancient sailors understood their own oceans. We know the distances to thousands of stars, the composition of nebulae, the motion of the galactic centre, all without leaving our solar system, all by collecting and analysing light. The impact of understanding galactic scale is to recognise that this method, observation from a distance, isn't a second, best option. It's the only option, and it's remarkably powerful. We can map the entire observable universe, billions of light years in every direction, without ever leaving Earth's vicinity. We can study galaxies so distant their light has been travelling since the universe was young. We can observe the cosmic microwave background, the afterglow of the Big Bang itself. None of this requires crossing distances. It only requires patience and sophisticated instruments. Telescopes instead of spacecraft. Spectroscopy instead of sample return missions. The impact is philosophical as well as practical. It forces us to ask, what is exploration for? Is it about physically going to places? Or is it about increasing knowledge, understanding more deeply, satisfying curiosity? If the goal is knowledge, then we're already succeeding spectacularly. We know more about the galaxy now than we did a century ago by factors of millions. And we're learning more every year. If the goal is presence, being there physically, then we're confronted with limits. The galaxy is too vast, the distance is too great. Physical presence at distant locations may be impossible, at least for beings like us. The impact of this realization is to shift our dreams. Instead of imagining missions to the far side of the galaxy, we imagine better telescopes, more sensitive instruments, cleverer analysis techniques. Instead of planning journeys of millions of years, we plan observations of distant regions, understanding that the light reaching us is already ancient, that we're seeing the galaxy not as it is but as it was. This shift doesn't diminish the ambition. If anything, it focuses it. Because if we can't cross the galaxy physically, then understanding it completely becomes even more important. Mapping every star, cataloguing every planet, understanding the mechanisms of star formation, galactic rotation, the evolution of spiral structure. These goals are achievable, difficult, requiring decades or centuries of work, but achievable, and they satisfy the same curiosity that drives exploration, the desire to know, to understand, to place ourselves in context. The impact also changes how we think about our future. If humanity persists for thousands or millions of years, what will we become? Will we spread outward, slowly colonizing nearby stars? Will we remain primarily on Earth, exploring through increasingly sophisticated remote sensing? Both paths are possible, and neither requires crossing the entire galaxy. We can imagine human presence expanding across a sphere, perhaps hundreds of light years in radius over the next million years. That's a tiny fraction of the galactic disk, but it's still thousands of star systems. Or we can imagine humanity remaining more localized, focusing on deep understanding of our local region rather than broad expansion. The impact of understanding galactic scale is to make both visions seem reasonable, not the grand dream of spanning the Milky Way, but the more modest dream of understanding our neighbourhood and perhaps expanding into it gradually. There's also an impact on how we think about other civilizations. If the galaxy is too vast for us to cross, it's too vast for them as well. Any other intelligent species faces the same limits. The same calculation that shows crossing is effectively impossible. This means the galaxy, if it contains other civilizations, is probably not unified. There's no galactic empire, no federation spanning the spiral arms. Instead, there might be scattered pockets of intelligence, separated by distances too great to bridge. Each civilization would be isolated, exploring its local region, perhaps aware of others through signals but unable to visit, unable to make contact beyond one-way messages taking thousands of years to arrive. The impact of this realization is both lonely and reassuring. Lonely because it suggests we might never meet other intelligences, never confirm we're not alone. Reassuring because it means we're not being visited, not being ignored, not missing out on some galactic community that exists everywhere but hasn't reached out to us. The galaxy is vast enough that intelligence can exist without interaction, and that vastness is what shapes both our possibilities and our limitations. The impact reaches into culture as well. Science fiction has long featured galactic empires, hyperspace travel, casual journeys between stars. These stories are valuable for exploring ideas, for imagining futures, for entertainment, but understanding the true scale of the galaxy gives us a different kind of story. Stories about patience, about long journeys, about societies that persist across generations, about the isolation of distance, about what it means to know you'll never reach the places you can see. These stories might be less dramatic, but they're more honest, and there's power in honesty, in facing the reality of scale rather than imagining ways around it. The impact also touches on meaning. Some people find the vastness of the galaxy discouraging. If we're so small, if the distances are so large, if we can't cross even our own cosmic neighbourhood, then what's the point? But another perspective is possible. The vastness makes our achievements more remarkable. That from one small planet, using light and mathematics, we've mapped structures too large to traverse. That we can know what we cannot reach. That we can understand distances beyond our scale. This capacity for knowledge, for comprehension beyond experience, is perhaps humanity's most distinctive trait. And the galaxy's vastness doesn't diminish it. The vastness highlights it, makes it more impressive, more meaningful. The impact of understanding galactic scale is ultimately about adjusting our dreams to reality, not abandoning them, but reshaping them. Recognizing that exploration doesn't require crossing, that knowledge is its own achievement. That understanding the galaxy is possible even when traversing it isn't. This adjustment is ongoing. Each generation inherits slightly different dreams, shaped by the knowledge accumulated before them. As we learn more about the galaxy, as we refine our measurements, as we send probes farther into space, our sense of what's possible evolves. The impact isn't static, it's dynamic. A continuing conversation between our ambitions and our limits. Between what we dream and what physics allows. Between the desire to reach out and the recognition that some distances are too vast even for the fastest travellers. But through all of this, the core impact remains. We live in a galaxy too large to cross, and rather than being a source of despair, this can be a source of perspective, a reminder that we're part of something vast. That our significance lies not in dominating distance but in comprehending it, not in conquering the galaxy but in understanding our place within it. The dreams have been reshaped, but they haven't disappeared. They've sighed, become richer, more nuanced, more grounded in reality. And in that grounding, they've become more meaningful, because dreams that acknowledge limits are stronger than dreams that ignore them. The impact continues to unfold as our technology advances. Each new telescope reveals more detail. Each probe that ventures outward extends our reach slightly, and with each extension, our understanding deepens. We may never cross the galaxy, but we're crossing it in a different sense. Through observation, through analysis, through the patient accumulation of light gathered from across 100,000 light-years of space. That crossing, intellectual rather than physical, is already complete in many ways. We know the Milky Way. We understand its structure. We've mapped its contents. And that knowledge, hard-won over centuries, is itself a form of exploration that acknowledges the limits while transcending them. The impact of understanding we cannot physically cross the galaxy is to recognize that we've already crossed it in the way that matters most. We've made it knowable. We've brought the distant close through comprehension, and in that achievement, the dream of galactic exploration is fulfilled, just not in the way we originally imagined. There's something profound we often forget when thinking about crossing the galaxy. We imagine it as a journey we might undertake someday, a mission to be planned and executed. But the truth is, we're already travelling. Right now, this very moment. We're not stationary. We never have been. Earth orbits the Sun at about 30 kilometers per second, and the Sun itself, carrying Earth and all the planets, orbits the centre of the Milky Way at approximately 230 kilometers per second. 230 kilometers every second. In the time it takes to read this sentence, the Sun has carried us more than 1,000 kilometers through the galaxy. We're already in motion, already making a journey, not one we chose or planned, but one we're part of simply by existing here, in this solar system, in this moment. The Sun's orbit around the galactic centre takes approximately 230 million years to complete. That's one galactic year, one full circuit through the spiral. The last time the Sun was in its current position, dinosaurs dominated Earth. The Triassic period was giving way to the Jurassic. Mammals existed, but only as small, shrew-like creatures. Flowering plants hadn't evolved yet. The continents were joined in the supercontinent Pangaea. Since then, the solar system has moved completely around the galaxy once. Pangaea broke apart. Dinosaurs rose to dominance and then went extinct. Mammals diversified, humans evolved, civilization emerged. And through all of this, the Sun carried us on its endless orbit. We are walkers beside the Sun, passengers on a vessel we didn't build, making a journey we didn't choose, moving through the galaxy at speeds we cannot control. This perspective changes how we think about galactic travel. We're not separate from the galaxy, looking in from outside. We're embedded within it, moving through it constantly, already participants in its motion. The Sun's path isn't a simple circle. It's more complex. As the Sun orbits, it also oscillates up and down through the galactic plane, like a wave. Every 30 million years or so, the solar system crosses through the midline of the disk. Right now, we're slightly above the plane, moving upward. In another 10 or 15 million years, we'll reach the peak of our oscillation, then begin falling back down. This bobbing motion takes us through different densities of gas and dust, different environments, different regions of the disk. Some scientists have speculated that these oscillations might correlate with events on Earth. Perhaps when we pass through denser regions of the disk, cosmic ray exposure increases, affecting climate or evolution. The evidence is debated, but the possibility reminds us that our motion through the galaxy isn't irrelevant to life on Earth. We're not just moving with the Sun, we're interacting with the galaxy as we move through it, passing through different neighborhoods, experiencing different conditions, shaped by our environment in ways we're only beginning to understand. Walking beside the Sun also means we've covered enormous distances. The Sun moves about 7 billion kilometers per year relative to the galactic center. Over the course of a human lifetime, that's hundreds of billions of kilometers. You have traveled farther through the galaxy than you'll ever comprehend. Not by choice, not by effort, simply by existing. Every moment of your life has occurred in motion, racing through space at hundreds of kilometers per second. This realization is grounding. When we talk about crossing the galaxy, we imagine building ships, launching missions, traveling vast distances. But we're already traveling vast distances. We're already crossing the galaxy, just very slowly. At the Sun's current speed, completing a full diameter crossing from one side of the disk to the other would take about 430 million years. That's longer than complex life has existed on Earth. But it's happening. The Sun is making that crossing, incrementally, inexorably. We won't see it complete. No human civilization will. But the journey continues regardless of our awareness. There's something humbling about being walkers beside the Sun. We have no control over this motion. We can't steer the Sun. We can't speed it up or slow it down. We're passengers on a vessel piloted by gravity, following an orbit determined by the mass distribution of the entire galaxy. Our agency is limited to small scales. We can explore the solar system. We might someday visit nearby stars. But the larger motion, the great orbit around the galactic center, is beyond our influence. And yet, this lack of control doesn't diminish us. If anything, it situates us, properly. We're part of a system larger than ourselves, subject to forces we can measure but not command, embedded in a structure that was here long before us and will persist long after. Walking beside the Sun also means we share the journey with everything on Earth. Every person, every animal, every plant, every microbe, all of us together, on this small planet, orbiting a star that orbits the galaxy. We're a travelling ecosystem, a mobile biosphere. Life exists not on a fixed platform, but on a vessel in motion, carrying billions of years of evolutionary history through the spiral arms of the Milky Way. When we look up at the night sky and see the Milky Way's band of light, we're seeing our path. The disk we're embedded in, the structure we're orbiting within. Every star in that glow is a fellow traveller, each on its own orbit, each moving at its own pace. Some stars move faster than the sun, some slower, some are overtaking us, some we're overtaking. The galaxy is not static, but flowing, a river of stars in constant motion. Walking beside the sun means accepting that we're part of this flow, not observers watching from outside, but participants swept along with billions of other stellar systems. This perspective makes the question of crossing the galaxy less urgent. We're already crossing it, in the only way that matters, not from edge to edge in a straight line, but in the great circular path that all stars follow. The crossing isn't something to achieve, it's something we're already doing. And we'll continue doing it as long as the sun burns, as long as Earth orbits, as long as life persists on this small world moving through the vast spiral. There's peace in this recognition. The galaxy doesn't need to be conquered or traversed by our spacecraft. It's already our path. We're already on the journey. Every moment of every life is a moment in motion through galactic space. Walking beside the sun teaches us patience. The orbit takes 230 million years. Completing even a fraction of it exceeds any human time frame. But the orbit continues regardless. Timescales that seem impossibly long to us are routine to the galaxy. Perhaps that's the lesson, that our brief lives are flashes in a much longer story. That we're part of a journey that began before life existed on Earth and will continue after we're gone. That walking beside the sun isn't something we choose, but something we simply are. The human element in crossing the galaxy isn't about building ships or achieving high speeds. It's about recognizing that we're already part of the crossing, already moving, already traveling through the very structure we imagine traversing. And in that recognition, there's both humility and wonder. Humility because we're not in control of the journey. Wonder because we're conscious participants in it, able to measure our motion, able to understand our path, able to know that we're walking beside the sun on its endless orbit through the Milky Way. This is our journey, not chosen but inherited, not planned but inevitable, not fast but constant, and it's enough, more than enough, because it connects us to the galaxy in the most fundamental way possible. We're not visitors to the Milky Way, we're residents, not observers of its motion but part of it. Walking beside the sun, we cross the galaxy in the only way that truly matters. By being here, by moving with it, by existing as conscious participants in its great rotation. The human element isn't about overcoming distance. It's about recognizing we're already immersed in the very thing we seek to understand. Already traveling through what we imagine crossing, already home in the place we dream of exploring. Walking beside the sun also means inheriting its history. The sun formed 4.6 billion years ago from a cloud of gas and dust enriched by previous generations of stars. The atoms in our bodies were forged in stellar furnaces, scattered by supernovae, and gathered into this solar system. We're not just walking beside the sun. We're made from the same cosmic material, recycled through stellar life cycles, shaped by the same galactic processes. Our journey isn't separate from the sun's journey. It's continuous with it. Every atom in your body has been on this orbit for billions of years, through countless cycles, mixing and reforming, but always moving, always part of the great circulation through the galaxy. To walk beside the sun is to walk within the sun's heritage, to be part of a story that began in stellar cores and continues in the complexity of living things orbiting through space. That continuity, that connection between stars and life, between galactic motion and human existence, is perhaps the deepest truth about our place in the Milky Way. If we're looking for reasons why crossing the galaxy is impossible, we don't need to look far. Physics itself stands in opposition, not as an adversary to defeat, but as an immutable framework that defines what can and cannot be. The limits aren't arbitrary, they're not technological barriers waiting for better engineering. They're fundamental features of the universe, written into the equations that govern space-time, energy, and motion. The first and most absolute limit is the speed of light, 300,000 kilometers per second. Nothing with mass can reach it. Nothing can exceed it. This isn't because we lack sufficiently powerful engines, It's because the structure of space-time itself forbids it. Einstein's relativity explains why. As an object accelerates toward light speed, several things happen. Its mass effectively increases, requiring ever more energy to accelerate further. Time slows for it relative to stationary observers, and the energy needed to continue accelerating approaches infinity. At light speed, the energy requirement becomes infinite. Literally, not just very large, but unbounded. And since infinite energy doesn't exist, neither does motion at light, speed for objects with mass. This limit is absolute. It has been tested thousands of times in particle accelerators. We can accelerate particles to 99.9999% of light speed, but never to 100%. The closer we push, the harder it gets. The curve approaches the limit asymptotically, always getting closer but never reaching. For galactic crossing, this means 100,000 years is the absolute minimum. Light makes the journey in that time. Nothing can do it faster. The limit is set not by technology, but by the universe itself. The second limit is energy. Even reaching a fraction of light speed requires enormous amounts of energy. To accelerate 1 kilogram to 10% of light speed requires about 400 trillion joules of energy. That's roughly the energy yield of 100 tons of TNT. For every kilogram, a spacecraft large enough to carry humans might mass hundreds of thousands of kilograms. Accelerating it to even 10% of light speed would require energy equivalent to thousands of nuclear weapons. And that's just to get going. You'd need similar energy to slow down at the destination. Where does that energy come from? Chemical rockets can't provide it. The energy density isn't high enough. Nuclear fission might help, but even that falls short at high fractions of light speed. Antimatter theoretically could. When matter and antimatter annihilate, they convert mass directly to energy with 100% efficiency. But we don't know how to produce antimatter in useful quantities, and we definitely don't know how to store it safely. The energy limit isn't absolute like the speed limit. In principle, if you had enough energy, you could accelerate to high speeds. But practically, the amounts needed are so vast they seem impossible, and that makes the limit real, even if not fundamental. The third limit is time. Even if you could reach high speeds, even if time dilation shortened the grooves, subjective journey, crossing the galaxy still takes massive amounts of objective time. Time that the rest of the universe experiences even if you don't. This creates a form of isolation that's as absolute as any physical barrier. Once you leave, travelling at near light speed, you're cut off. Communication takes years or millennia. You're moving through time as well as space, arriving in a future where everything you knew is gone. This temporal limit doesn't prevent travel physically, but it makes it meaningless in certain ways. If you arrive in a galaxy where your civilization has been extinct for thousands of years, have you really completed a journey? Or have you just exiled yourself permanently? The fourth limit is reliability. Spacecraft fail, components wear out, systems degrade. The longer a journey takes, the more likely something critical will break. For a journey of hundreds of thousands of years, every component must either last that long or be repairable. But we don't know how to make anything that lasts hundreds of thousands of years. The oldest human artifacts are a few thousand years old, and they're broken, degraded, barely functional. A generation ship would need to maintain all its systems for timescales longer than human civilization has existed. The engineering challenges are profound, not because we can't imagine solutions, but because we can't test them. We can't verify that something will work for 100,000 years because we don't have 100,000 years to test it. The fifth limit is biological. Humans are adapted to Earth, to its gravity, its atmosphere, its magnetic field, its day length, its ecosystem. Remove those conditions and problems emerge. In microgravity, bones weaken and muscles atrophy. In cosmic radiation, cancer risks increase. In isolation, psychological problems develop. These aren't insurmountable in principle, but they add complexity. And over generational timescales, biology evolves. A population living for thousands of generations in a completely different environment would likely change. Genetically, physically, psychologically. Would they still be human in any meaningful sense? Or would they become something else? The biological limit isn't that humans can't survive in space, it's that humans might not remain human over the timescales required. The sixth limit is practical. Why cross the galaxy at all? What's the goal? If it's knowledge, we can gain that through observation. If it's resources, the solar system contains more than we could use in millions of years. If it's survival, spreading to nearby stars seems more practical than attempting a full crossing. The practical limit is that even if we could cross the galaxy, there's no compelling reason to do so. The cost would be enormous, the benefit unclear, and the opportunity cost, all the things we could do instead with that energy and effort, would be staggering. These limits combine to create a wall. Not one limit, but many, each reinforcing the others. To cross the galaxy, you'd need to overcome all of them simultaneously. Speed, energy, time, reliability, biology, and purpose. And even if you solved all of those, you'd still be up against the fundamental physics. The speed of light remains absolute, 100,000 years at minimum. Nothing changes that. The opposition isn't malicious. Physics doesn't care about our dreams. It simply is. The laws of nature operate indifferently, defining what's possible and what isn't with perfect neutrality. Understanding these limits isn't defeatism, it's realism. It's recognizing that some boundaries are not meant to be crossed because they're not boundaries in the sense of walls we might breach. They're definitions, features of reality itself. The speed of light doesn't oppose us, it defines the structure of space-time. The energy requirements don't block us. They reflect the relationship between mass and velocity. The temporal isolation doesn't prevent travel. It reveals the nature of time. These aren't obstacles to overcome, they're facts to accept. And in accepting them, we can make better decisions about what to pursue. If crossing the galaxy is fundamentally impractical, then focusing on local exploration makes sense. If light speed is absolute, then investing in observation rather than travel makes sense. The opposition of physics isn't the end of dreams, it's the beginning of wisdom. Knowing what's impossible allows us to focus on what's possible, and what's possible, within the limits physics imposes, is still remarkable. We can explore the solar system. We can send probes to nearby stars. We can observe the entire galaxy from where we are. We can understand cosmic structure without traversing it. Physics limits us, but it also enables us. The same laws that prevent faster than light travel also make stars shine, make planets stable, make life possible. The limits and the possibilities come from the same source. The opposition isn't something to fight, it's something to work within, to understand, to respect. And in that respect, we find not limitations but a framework, a set of rules that makes the universe knowable, predictable, comprehensible. The galaxy is too vast to cross because physics says so, and physics is right, not because it's mean or restrictive, but because it's true. The limits are real, the opposition is absolute, and accepting that allows us to move forward with clarity, focusing our dreams on what's achievable rather than wasting energy on what's not. The limits of physics also give us something valuable: certainty. We know the speed of light won't change, we know the energy equations are reliable. We know time dilation works exactly as predicted. This certainty means we can plan meaningfully. We can calculate journey times with confidence. We can design missions knowing they won't suddenly become easier because some fundamental law shifted. The opposition is stable, predictable, and in that, predictability lies a kind of comfort. The universe has rules. Those rules limit us, yes, but they also make science possible, make engineering reliable, make predictions meaningful. Without the opposition of physics, without the limits that constrain us, we'd have no foundation for knowledge. The very limits that prevent us from crossing the galaxy are the same limits that allow us to understand it, measure it, know it with precision. The opposition isn't our enemy, it's our teacher, and what it teaches is that some questions have definitive answers. Crossing the galaxy takes 100,000 years at light speed. That's not negotiable, and knowing it allows us to stop hoping for miracles and start working with reality. Even when physics stands in opposition, even when the limits seem absolute, the human mind continues to search for alternatives, for loopholes, for ways around the barriers rather than through them. This is where the dreams of shortcuts awaken. Not practical plans, not imminent technologies, but theoretical possibilities that physics allows, at least on paper, even if engineering doesn't know how to realize them. The most famous shortcut is the wormhole. Einstein's equations permit solutions where space-time folds back on itself, creating a tunnel between distant points. Enter one mouth of the wormhole, emerge from the other, having crossed the intervening space without travelling through it. The concept is elegant. Instead of moving through space, you move through a shortcut in space-time itself. The distance from one side of the galaxy to the other might be 100,000 light-years through normal space, but only a few meters through a wormhole. The mathematics works. The solutions exist, but the requirements are extreme. To create a traversable wormhole, you'd need exotic matter with negative energy density. This isn't ordinary matter. It's something that pushes outward rather than pulling inward, that has properties opposite to everything we've ever observed in nature. Small amounts of negative energy might exist in quantum effects like the Casimir force, but creating enough to hold open a wormhole would require amounts far beyond anything we can produce or imagine producing. And even if you could create a wormhole, keeping it stable while something passes through presents additional problems, the throat might collapse, the entrance might seal, the exotic matter might destabilize. Wormholes remain firmly in the category of allowed by equations but impossible in practice. They're a dream of a shortcut, not a path we can currently walk. The second famous shortcut is the warp drive. The Alcubierre drive, proposed in the 1990s, uses general relativity to compress space in front of a ship and expand it behind. The ship itself doesn't move. It sits inside a bubble of normal space. But the bubble moves, carrying the ship with it. Because the ship isn't moving through space but being carried by space, it can effectively travel faster than light without violating relativity. The ship remains stationary in its bubble. It's space-time that moves. Again, the mathematics allows it. But again, the requirements are impossible. You'd need vast amounts of negative energy to create the compression and expansion. The energy requirements, even with refinements to the original concept, remain astronomical, far beyond any conceivable power source. And there are causality problems. A warp drive might allow time travel under certain conditions, creating paradoxes. Many physicists suspect that if warp drives were possible, some undiscovered law of physics would prevent them, preserving causality. Warp drives are dreams, beautiful mathematical dreams, showing that relativity has strange solutions, but not practical pathways. The third category of shortcuts involves extra dimensions. String theory suggests the universe has more than the three spatial dimensions we perceive. Most of these extra dimensions are curled up, too small to notice. But some theories allow for larger extra dimensions or ways to access them. If you could move through a higher dimension, the distance between 2 points in our three-dimensional space might be much shorter. Like walking across a sheet of paper versus folding it to bring two edges together. This is speculative even by the standards of theoretical physics. We have no evidence for extra spatial dimensions beyond the mathematical framework of string theory, and even if they exist, we have no idea how to access them or move through them. Extra-dimensional shortcuts are dreams within dreams, possibilities that depend on unconfirmed theories requiring technologies we can't even conceptualize. The fourth shortcut is quantum. Quantum entanglement connects particles instantaneously across arbitrary distances. When you measure one particle, you instantly know the state of its entangled partner, no matter how far away it is. This seems to violate the speed of light limit. Information appears to travel faster than light, but it doesn't, quite. You can't use entanglement to send information. You can only observe correlations after the fact. No useful signal can travel faster than light through entanglement. Still, some dreamers wonder whether quantum mechanics might offer other shortcuts. Quantum tunneling allows particles to pass through barriers they classically couldn't. Might there be some quantum analog for large-scale travel, some way to tunnel through space itself? These ideas are highly speculative. Quantum effects dominate at small scales. Extending them to human-sized objects, let alone spacecraft, encounters enormous obstacles, but they represent another category of shortcuts the mind explores when faced with impossible distances. The fifth category is engineering-based, though still far beyond current capability. Solar sails pushed by powerful lasers, ion drives accumulating velocity over decades. Fusion rockets, burning hydrogen harvested from interstellar space. Antimatter drives if we ever learn to produce and store antimatter safely. These aren't shortcuts in space-time, but shortcuts in capability, ways to reach higher fractions of light speed than chemical rockets allow. Not fast enough to make galactic crossings quick, but fast enough to reduce journey times from billions of years to hundreds of thousands. These engineering shortcuts are dreams, but grounded dreams. Dreams based on physics we understand and engineering principles we know, even if execution remains beyond us. The awakening of shortcut dreams happens whenever we confront impossible distances. The mind refuses to accept no easily. It searches for alternatives, for loopholes, for creative solutions. This searching is valuable even when it doesn't yield practical answers, because in exploring possibilities, we deepen our understanding of physics. We test the boundaries of theories. We discover which parts of the equations are flexible and which are rigid. Wormhole research teaches us about space-time topology. Warp drive studies reveal connections between energy and geometry. Quantum explorations show us the limits of what's possible at different scales. The dreams of shortcuts are how we probe reality, how we ask, what if, and follow the mathematics to see where it leads. Most shortcuts remain dreams. Wormholes need exotic matter we can't make. Warp drives need energy we can't generate. Extra dimensions might not exist in accessible form. Quantum shortcuts probably don't extend to large scales. But the dreaming continues, because the alternative, accepting that 100,000 years at light speed is truly the minimum, feels limiting. The mind wants options, wants possibilities, wants to believe that somewhere in the vast structure of physical law there's a loophole. And maybe there is. Physics is still incomplete. We don't understand quantum gravity. We don't know what dark matter is. We don't fully grasp dark energy. Each of these unknowns might contain surprises. Perhaps in the complete theory of quantum gravity, shortcuts emerge naturally. Perhaps dark energy can be harnessed for propulsion. Perhaps dark matter has properties that allow interaction we haven't discovered. These are long-shot hopes. Wishes more than predictions, but they're not absurd. History shows that new physics often reveals new possibilities. Quantum mechanics enabled transistors, lasers, and computers. Relativity enabled GPS satellites. Nuclear physics enabled reactors and weapons. What might a complete understanding of quantum gravity enable? What technologies might arise from truly understanding dark energy? We don't know. We can't know. That's what makes them potential sources of shortcuts. The awakening of shortcut dreams is a response to limits. When faced with barriers, the mind seeks alternatives, and in that seeking, even when it doesn't find practical paths, it finds questions. Deeper questions. Better questions. Questions that drive physics forward. Shortcuts may remain forever out of reach. The galaxy may truly be too vast to cross except by enduring 100,000 years at light speed. But the dreams persist. Because dreams are how we explore possibility, how we test reality, how we refuse to accept that our current understanding is final. The shortcuts may be impossible, probably are impossible. But the dreaming isn't, and in that dreaming, we've learned more about space-time, energy, quantum mechanics, and the structure of the universe than we would have by accepting limits without question. So the dreams awaken. Wormholes and warp drives, extra dimensions and quantum tunneling, engineering marvels and exotic physics. Each one a possibility explored, A question asked, a boundary tested, and even if none of them work, even if the galaxy remains too vast to cross except by patience beyond human scale, the awakening matters, because it shows we're not content with impossible. We're curious, creative, persistent. The shortcuts may be dreams, but dreams shape reality. By imagining what might be, we discover what is. By exploring theoretical possibilities, we map the boundaries of the actual. By refusing to accept limits without question, we ensure that our understanding continues to deepen. The galaxy may not be crossable by any shortcut, but we've awakened to the possibilities. We've explored the mathematics. We've tested the theories. And in that exploration, we've learned something profound. That physics is rich, strange, and full of surprises. That the universe is more complex than we imagined. And that even when shortcuts don't exist, the search for them teaches us about reality. There's a revelation that emerges once you've explored all the calculations, considered all the shortcuts, and confronted all the limits. A simple but profound truth that reframes the entire question. Forever is relative. When we say, crossing the galaxy takes forever, we're measuring from a human perspective. From the viewpoint of beings who live decades, whose civilizations endure millennia, whose species has existed for hundreds of thousands of years at most. From that perspective, 100,000 years is forever. It's longer than our entire existence as conscious beings. It's a span that exceeds all memory, all history, all cultural continuity. But from other perspectives, 100,000 years is not forever. It's not even particularly long. From the galaxy's perspective, if we can speak of the galaxy having a perspective, 100,000 years is less than 1/10,000th of its age. The Milky Way is approximately 13 billion years old. 100,000 years represents about 0.0008% of that age. It's a blink, a moment, negligible. From a photon's perspective, as we've discussed, the journey takes no time at all, zero duration. The crossing happens instantly from the photon's reference frame, even though external observers measure 100,000 years. From a star's perspective, 100,000 years is brief. Stars like our Sun live for about 10 billion years. 100,000 years is 1/100th of 1% of that lifespan. A star born when the crossing begins would barely notice the passing by the time it ends. From a black hole's perspective, 100,000 years is utterly insignificant. Black holes can exist for trillions upon trillions of years, slowly evaporating through Hawking radiation. 100,000 years is too short to measure against such timescales. The revelation is that forever isn't absolute. It's a judgment we make based on our own temporal scale, and our scale, while real and meaningful to us, is extraordinarily brief compared to cosmic processes. This revelation doesn't make crossing the galaxy easier. The 100,000 years don't disappear because we recognize they're short, and on cosmic scales. From our perspective, they remain prohibitively long, but the revelation changes how we understand the problem. It shows us that the barrier isn't really about time. It's about mismatch. A mismatch between the timescales we exist on and the timescales the galaxy operates on. We live fast, the galaxy lives slow, and that difference is what makes crossing seem impossible. Consider it another way. If a human lifetime were 1,000,000 years, 100,000 years would feel manageable. Not quick, but conceivable. You could plan for it, prepare, experience the journey. But human lifetimes aren't 1,000,000 years, they're less than 100, by factors of 10,000, and that factor is what creates the sense of forever. The revelation extends beyond time to space. The galaxy is 100,000 light-years across. That sounds impossibly vast, but it's less than 1,000th the size of the observable universe. The observable universe spans about 93 billion light-years. The Milky Way's 100,000 light-years is tiny by comparison. From the universe's perspective, if we can imagine such a thing, the Milky Way is small. Crossing it is a local journey, not the vast expedition it seems to us, but a short hop between nearby points, Forever is relative not just to time but to space. The galaxy seems infinite to us because we're so small. But at larger scales, it's modest. Average. One galaxy among billions. None of them particularly special in size. The revelation also applies to speed. The speed of light seems impossibly fast to us. 300,000 kilometers per second. Fast enough to circle Earth 7 times in 1 second. But measured against galactic distances, light is slow, painfully slow. It takes 8 minutes just to reach Earth from the Sun. Over 4 years to reach the nearest star. 100,000 years to cross the galaxy. From light's perspective, if it could have one, it moves infinitely fast. From hours, it's the ultimate speed. From the galaxy's perspective, it's sluggish, insufficient, not fast enough to make the structure feel connected. This relativity of speed mirrors the relativity of time. What seems fast at one scale is slow at another. What seems forever at one scale is brief at another. There are no absolutes, only perspectives. The revelation invites a shift in thinking. Instead of asking, how long does it take to cross the galaxy, we might ask, how long relative to what? Relative to a human life. Forever. Relative to stellar lifespans. Brief. Relative to the galaxy's age. Instantaneous. Each answer is true. Each reflects a different frame of reference, and none is more valid than the others. They're all real perspectives on the same underlying fact. The 100,000 years to cross the galaxy is fixed. Objective. Measurable. But its meaning shifts depending on who's measuring and why. This revelation has implications for how we think about exploration. If we can't change the time it takes, perhaps we can change our relationship to that time. Not individually, we can't extend our lifetimes enough to matter, but collectively, a species that accepted generational timescales might find 100,000 years more conceivable. Not easy, but within the realm of planning. Not forever, but long, or we might change our goals. Instead of crossing, we explore. Instead of traversing, we observe. Instead of reaching the far side, we understand the structure from where we are. These alternative goals don't require escaping the relativity of forever. They work within it. They accept that from our perspective, certain things take too long, and they find value in what's possible within our timescale. The revelation is humbling. It shows us that our perspective isn't privileged, that the galaxy doesn't care about human lifespans, that cosmic structures operate on their own scales, indifferent to ours. But the revelation is also liberating. If forever it is relative, then our perception of impossibility is also relative. What seems impossible from one viewpoint might seem different from another. We can't change our lifespans enough to make galactic crossings feel short, but we can change our frame of reference. We can think in terms of species rather than individuals, eons rather than years, evolutionary timescales rather than cultural ones. From those frames, 100,000 years is still long. But it's not forever. It's finite, measurable, conceivable. The revelation doesn't solve the problem of crossing the galaxy, but it reframes it. It shows that the problem isn't the distance or the time. It's the scale mismatch. And scale mismatches are problems of perspective as much as physics. Forever is relative. That's the revelation. Simple but profound. And once you see it, you can't unsee it. The galaxy remains vast. The crossing remains difficult. But the sense of impossible forever softens into something else. Not quick. Not easy. But not eternal either. Just very, very long compared to us. And in that comparison lies both the challenge and the opportunity. The challenge to think bigger, to stretch our temporal imagination, to conceive of projects that outlast individuals, and the opportunity to recognize that what seems forever to us is merely time to the universe, that our brief lives are flashes in a much longer story, that we're part of processes operating on scales we don't personally experience but can still comprehend. Forever is relative, and in that relativity we find both our limits and our capacity to transcend them. Not physically, we can't cross the galaxy, but conceptually, by understanding that the crossing takes 100,000 years objectively, forever subjectively, and no time at all from the viewpoint of eternity. All three are true, all three matter, and holding all three perspectives simultaneously is what it means to truly understand the scale of our cosmic home. The revelation of relativity extends to meaning as well. What does it mean to cross the galaxy? From a human perspective, it means achieving something impossible. From a photon's perspective, it means nothing, the journey doesn't register. From the galaxy's perspective, it means a slight rearrangement of components within its structure, meaning, like time, is relative. We project significance onto events based on our scale. The crossing seems profound to us because it exceeds our capabilities, but the universe doesn't mark it as special, doesn't celebrate or mourn. It simply continues, indifferent to whether any particular species spans particular distances. The revelation is that significance is something we bring, not something inherent. The galaxy doesn't care if we cross it, but we care. And that care, that assignment of meaning to a crossing that from cosmic perspectives is trivial, is itself profound. It shows that consciousness, however brief, creates meaning where none existed, that we can take an objective fact 100,000 light years and imbue it with significance, making it a question worth asking, a goal worth contemplating, a dream worth holding even when unachievable. When we imagine crossing the galaxy, we often picture travelling from star to star, passing through systems, seeing suns and planets, experiencing the richness of the Milky Way's stellar population. But the reality is different. Most of any galactic crossing would be spent not near stars, but between them. In the vast, empty spaces where nothing shines, where silence reigns, where darkness is absolute. This is the reflection we must consider, that the galaxy, for all its billions of stars, is mostly empty, and any journey across it would be defined not by the destinations but by the void between them. The average distance between stars in our region of the galaxy is about 4 light years. That's the typical spacing in the disk, where stellar density is moderate. In some regions, stars are closer, in others, farther apart. 4 light years, that's about 40 trillion kilometers of emptiness, between each island of light and ocean of darkness. If you could travel at 10% of light speed, an enormous achievement crossing from one star to the next would take 40 years. And that's to reach the nearest neighbour. Most stars are farther. Many are tens of light years distant. The journey would be defined by those 40-year gaps, decades of travelling through nothing, seeing the star you left behind recede slowly, seeing the star ahead approach gradually. But for years or decades in between, just darkness. And that's between stars in our neighbourhood. To cross the entire galaxy, you'd encounter thousands upon thousands of such gaps, spending most of your time in interstellar space, far from any sun, surrounded by the cold and the quiet. The silence between stars is literal. In space, there's no medium to carry sound. But it's also metaphorical. There are no signals, no transmissions, no evidence of other civilizations, at least none we've detected. The galaxy is filled with stars, yet eerily quiet. We send radio telescopes searching for artificial signals. We scan the sky for signs of intelligence, and we find nothing. Only natural sources, pulsars, quasars, gas clouds, but no voices. This silence is part of what makes the galaxy feel empty despite its population of billions of stars. It's not just physically empty between stars, it's informationally empty, void of messages, void of contact. For travellers, this silence would be profound, not just physically isolated, but informationally isolated, far from Earth, beyond the range of communication, with no other signals to pick up, just the spacecraft, its crew, and the darkness. The psychological impact would be severe. Humans are social. We're adapted to communication, to connection, to knowing that others are near. To be truly alone in the silence between stars might break something fundamental in the human psyche. Some proposals for generation ships include extensive virtual environments, simulations of Earth landscapes, digital libraries containing all human knowledge, art, music, culture, preserved in data. Anything to fill the silence with meaning, but these are substitutes, echoes of home, not the real thing. And over generations, their significance might fade. The descendants might not feel connected to simulated Earth forests. They might develop their own culture, suited to the ship, adapted to the silence. The silence between stars also reflects a deeper truth about the galaxy. It's not a bustling metropolis of civilizations. It's not a place where intelligent species casually interact across light years. If other civilizations exist, they're separated by distances that prevent interaction, each one isolated in its local neighborhood, perhaps aware of others through ancient signals but unable to communicate meaningfully. The silence might not be because civilizations are rare. It might be because the galaxy is too vast for connection. Each species isolated by the same distances that isolate us, each facing the same silence. This possibility is both lonely and logical. The galaxy's scale naturally creates isolation. Even if intelligence is common, communication is difficult, and travel is impossible. So civilizations arise, persist, and fade, each in its own pocket of the spiral, never truly touching. The silence also makes the stars themselves more precious. When you're surrounded by emptiness, the occasional star becomes a beacon, not just a source of light and heat, but a landmark, a point of reference in the void. Navigators crossing the galaxy would measure their progress by stars. Each system passed would be a milestone, a confirmation that they're still moving, still making progress through the silence. But between those milestones, years would pass, decades, generations, all spent in the quiet dark, with only memory and hope to sustain them. The reflection on silence also invites us to consider what we're missing. Our observations of the galaxy are limited to light and other electromagnetic radiation. We see stars because they shine. We detect gas clouds because they absorb or emit. But we don't see the spaces between. We don't observe the pure vacuum. We can measure it indirectly, count the atoms per cubic centimetre, note the occasional grain of dust, but we don't experience it. To cross the galaxy would be to experience that void directly, to understand viscerally what emptiness means on cosmic scales, to feel the silence not as absence of sound, but as absence of everything except the rare photon passing through. That experience might be transformative, or it might be maddening. We don't know. We've never been truly isolated from the sun, from Earth, from the web of signals that connect us to home. The longest anyone has been in space is about a year on the International Space Station, still orbiting Earth, still in communication, still bathed in sunlight for half of each orbit, still connected. To be between stars would be different. No sun overhead, no planet below, no signals except what you carry. Just the ship, the crew, and the void. The silence between stars is the cost of crossing, not measured in energy or time alone, but in isolation, in the acceptance that most of the journey is emptiness, that the galaxy's structure, billions of stars, is also defined by the incomprehensibly larger volume of nothing between them. And perhaps that's the most important reflection, that the galaxy isn't its stars, it's the space between them, the structure that holds them apart, the distances that make each star an island. We think of the Milky Way as full of stars, full of life, full of possibilities. But by volume, it's almost entirely empty. The stars are rare accidents in a sea of vacuum. The silence is the default state. Crossing the galaxy means crossing that. Silence, enduring it, finding meaning within it, despite its emptiness. And that might be the hardest part. Not the time or the speed or the energy, but the silence itself, the quiet between stars where nothing breaks the monotony except the slow passage of time and the gradual approach of the next distant sun. The silence also carries a kind of beauty. In the absence of everything else, the stars themselves shine more brightly. Not literally, their luminosity doesn't change, but perceptually, against absolute darkness, any light becomes precious. The silence makes the stars matter more, makes each encounter with a system more significant, makes the goal of crossing more meaningful because of what must be endured to achieve it. In the quiet between stars, thoughts echo. Time stretches. The mind turns inward because there's nothing external to focus on. That inward turning might be enlightening, or it might be destructive, but it would definitely be profound. The silence would force contemplation, meditation, a confrontation with existence in its most minimal form. Just consciousness, duration, and void. Perhaps that's what crossing the galaxy truly means. Not travelling through a rich tapestry of stellar systems, but traversing the silence that separates them, learning to endure emptiness, finding purpose in the absence of stimulation, becoming comfortable with the void. The galaxy teaches this lesson whether we cross it or not. Because even from Earth, when we look at the night sky, most of what we're seeing is the space between stars, the darkness punctuated by points of light, the silence interrupted by signals, and in that observation, we're already experiencing, at least visually, what travellers would experience directly, the profound emptiness, the rare islands, the structure defined as much by absence as by presence. As this night draws toward its close, as your breathing has slowed and your thoughts have drifted through distances measured in light years, and time measured in epochs, we return to where we began. Not to a conclusion, because questions of scale don't truly conclude, but to a recognition, a settling. We've asked how long it would take to cross our galaxy, and we've found many answers, each true from its own perspective. 100,000 years at light speed, billions of years at spacecraft speeds, hundreds of thousands of years with speculative technologies, subjectively shorter with time dilation, but only at speeds we don't know how to achieve. We've explored shortcuts that remain dreams, wormholes requiring exotic matter, warp drives needing impossible energies, extra dimensions that might not exist, quantum paths that probably don't scale. We've confronted limits. The speed of light is absolute. Energy requirements are enormous. Time stretches whether we experience it subjectively or not. Reliability over such spans is questionable. Biology adapts or degrades. Purpose fades across generations. And through all of this, one truth has emerged clearly. We will not cross the galaxy. Not as individuals, not as civilizations in any form we'd recognize. The distances are too vast, the time too long, the challenges too fundamental. But this truth, this recognition of limits, doesn't diminish us. If anything, it situates us properly, places us in context, shows us where we belong in the vast spiral we inhabit. We belong here, not at the galactic center, not racing across its arms, but here in the Orion arm, orbiting a yellow star at a comfortable distance from the core. This is our home, not just Earth, not just the solar system, but this region of the galaxy. The local neighborhood of stars within a few dozen light years. The volume we can observe, the structure we can measure, the space we exist within. And from this home, we've achieved something extraordinary. We've mapped the galaxy. We've measured its size, traced its spiral structure, located its center, estimated its mass, understood its rotation. We've done this without travelling, without leaving our solar system, let alone crossing to distant arms. We've done it with light, with patience, with mathematics, with instruments that gather photons that have travelled for thousands of years to reach us. That achievement is profound. We know the Milky Way. We understand its shape, its age, its contents. We know where we are within it. We know how we move through it, orbiting the centre at 230 kilometers per second, bobbing up and down through the disk. We know that Sagittarius A star, a supermassive black hole 4 million times the Sun's mass, anchors the centre. We know that dark matter, invisible but measurable through its gravity, dominates the mass distribution. We know that stars are born in nebulae, live for billions of years, and die in supernova explosions or quiet fades to white dwarfs. We know that spiral arms are density waves, not fixed structures. We know that the galaxy rotates differentially, with inner regions moving faster than outer ones. We know that it's cannibalizing smaller galaxies, leaving streams of stars as evidence of ancient collisions. All of this knowledge, all of this understanding, comes from staying home and observing, from collecting light rather than travelling to its sources, from being patient rather than rushing outward. And perhaps that's the most important realization. That exploration doesn't require traversing every distance. That understanding doesn't demand physical presence. That we can know without going, comprehend without touching, appreciate without possessing. The galaxy is our home. We're embedded within it, moving through it, made from its material. Every atom in our bodies was forged in stars, scattered by supernova, and collected into the solar system. We're literally made of galaxy, part of its substance, part of its story. This belonging is deeper than location. It's compositional. We're not visitors to the Milky Way, manifestations of it. Local concentrations of complexity that arose from its processes and persist within its structure. When we ask how long it would take to cross the galaxy, we're really asking how long it would take to traverse the very thing we're made of, to move through the structure that created us. And the answer, fittingly, is longer than we exist. We can't cross it because we're part of it. Our timescale is nested within its timescale. Our motion is embedded in its motion. We're not separate entities attempting to traverse an external distance. We're components of the galaxy, trying to comprehend the whole, and we can comprehend it. That's the gift. That's the achievement. From our small vantage point, using the tools of science and mathematics, we can understand structure that exceeds our grasp. We can measure what we cannot traverse. We can know what we cannot reach. This capacity for knowledge beyond experience is perhaps humanity's defining trait. We exist in a tiny corner of a vast galaxy, but we can think across its entire span, map its spiral, trace its history, predict its future. The galaxy will merge with Andromeda in a few billion years. The sun will exhaust its hydrogen and swell into a red giant, engulfing Earth. The Milky Way's structure will be radically different. Eventually, after trillions of years, the last stars will fade. The black holes will evaporate. The galaxy will dissolve into darkness. We won't be here for any of that. Humanity's future is measured in millions of years at most, perhaps thousands if we're unlucky. But we can know the galaxy's full story anyway. From beginning to end, we can hold its entire 13 billion year past and its trillions of years of future in our minds. That's what it means to be home among the stars, to be small but aware, brief but comprehending, limited in reach but unlimited in thought. We cannot cross the galaxy, but we can hold it, not in our hands, but in our understanding. We can know its scale, appreciate its vastness, recognize our place within it, and in that recognition, there's peace. The galaxy doesn't need to be crossed to be known. Distance doesn't need to be traversed to be measured. The impossible doesn't need to be achieved to be contemplated. We're home, here in the Orion Arm, orbiting an ordinary star, part of a galaxy too vast to cross but not too vast to comprehend. This is enough, more than enough, to exist within something larger than ourselves, to be part of a structure that exceeds our individual scope, to know, even briefly, what it means to be conscious in a universe of such scale. The galaxy stretches around us, 100,000 light years from edge to edge, billions of stars, trillions of planets, vast clouds of gas and dust, structures beyond complete description, all of it rotating slowly, evolving gradually, existing on timescales that dwarf ours. And we're here, aware of it, measuring it, understanding it, making it known to ourselves through the patient work of observation and thought. How long would it take to cross our galaxy? 100,000 years at light speed. But we don't need to cross it. We already live within it. We're already home among the stars, already part of the structure we seek to understand. And that, perhaps, is the true answer. Not a time or a speed, but a recognition that crossing isn't necessary. that home is where we already are, that the galaxy, vast as it is not a distance to be traversed but a context to be appreciated. We're here, small and brief, but conscious, capable of asking questions that exceed our scale, capable of understanding answers that span eons and light years. The galaxy is our home, and we're learning, slowly, patiently, what it means to live in something so large, so old, so indifferent to our individual existence, but so rich in structure and history. How long would it take to cross it? Forever, by our measure. A moment, by cosmic standards, instantaneous from certain perspectives. All answers are true, all reflect different aspects of the same reality. But the deepest answer might be this: it doesn't matter, because we're not crossing. We're dwelling, living within, belonging to, understanding from here. And as you drift towards sleep, as your thoughts fade into rest, carry this with you. You're part of a galaxy, made from its material, moving with its motion, brief but real, small but aware. The Milky Way stretches overhead, a band of light across the darkness. You won't cross it, but you don't need to. You're already part of it, already home among the stars, already exactly where you belong. Sleep well, traveller. The galaxy continues its slow rotation, the sun continues its orbit, and you, here in this moment, are part of that cosmic motion, part of something vast, part of the crossing that's always happening, even when we stand still. Good night, and thank you for spending this time among the stars, asking questions that have no simple answers, finding peace in the vastness that surrounds us all.